That's Wigner's friend. Wigner is here. Now, this person measures the qubit. It's going to be up or down, right? But the postulates of quantum mechanics do not answer the following question. Did the qubit collapsed? Did the spin like collapse to up or down? Or is the person who reads the result now in a superposition too? Right? Because for the person outside, this is the quantum system.
Yeah. So do you want to jump right into it, or?
Sure. I just have a small disclosure. It's my first podcast ever.
Cool.
So let me just bound this. So because this is like a big board.
Yeah.
I want to know that if I write, I'm in the right bounds. Okay. You still can see inside the lines, right?
Yep.
Okay. All right. Yes, my idea is one thing I would like to discuss with you, because I've seen like what you talk about in your podcast is the wave function real, like here in the universe with us, or is it just information about the experiments that we do? But to do this right, I believe we need like the math, the tools behind this. So I'll be working with the simplest example of a wave function. That will be for qubits. You heard of qubits before?
No, what is that?
No, that's perfect. Like nobody heard of qubits. Like they know there's like quantum bits, but that's all we know. So a qubit, it's a quantum system that we call generally speaking, it's a two-level quantum system. But here we'll be working with this notation. This is called the Dirac notation for quantum states. Here what I'm doing is a ket. If I don't put anything inside, that's what we call a ket. And if I put something there, it means the zero ket. So I put the zero, it means it's a zero ket. If I do this, then it's a one ket. Right? We also call these states, the zero state, the one state. But what
are you saying?
Yeah.
Question: Are you saying cat, and is that relating to Schrodinger's cat? Is that where that term?
No,
comes
not
from?
cat. Ket.
Cat. Okay.
Yes, like this. Ket.
Okay.
Okay. Now we write this, and physicists write this to refer to any quantum systems, to like the quantum states of things. But what we actually mean when we write this is vectors. So let me start with the first one. If I write this, what I actually mean is like this vector, 1, 0. Two-dimensional vector, that means to be a two-level quantum system. You have two effective dimensions here. And for those who don't know what a vector is a list of numbers, right? And I'll tell you like how to operate with them. So because I want to make this for people who don't know like anything about linear algebra. So we will look like at the essentials. Now here, we also have the one state. And the one state will be the opposite of this, 0, 1. But in general, a quantum state, we denote it with a psi letter, the Greek letter. It's a general vector. So it will be something that has alpha and beta. These could be complex numbers, but we won't bother about that for now. And this, we can also write it as alpha times the 0 state plus beta times the 1 state. And if I write it down, like plugging in these definitions, I see alpha 1, 0 plus beta 0, 1. And here's where the operations with the vectors come into play. So here what we do is we multiply the constant that is outside the vector for every one of the entries. So this will be alpha times 1 is alpha, alpha times 0 is 0. Plus beta times 0, beta times 1, like this. And now we add vectors coordinate-wise, so that with alpha plus 0 is alpha, and 0 plus beta is beta, which is the same thing that we wrote here. So this part here is a compact way of writing down vectors. But now what happens? We need a measurement device to come out, because I think we've all heard that quantum mechanics is probabilistic. This is something that we say a lot. The outcomes are probabilistic, and that's famously Einstein saying, God doesn't play dice, right? So where's the dice in here? Well, the dice is on the alpha and the beta. There's one condition for a vector like this to be a valid quantum state. And is that, so the condition is that the absolute value of alpha squared plus the absolute value of beta squared is equal to 1. Now I'm putting here absolute values because this counts for when you have complex numbers. If you don't have complex numbers, if you only have real numbers, then with the squares is enough. And why this? Because look at this expression, right? We say that these two states are basis states. And they are basis states because any other two-dimensional vector, I can write it out in terms of 0 and 1. So any other thing that I write down like this, I can put it in this form, which is given in terms of these zeros and ones. Now, why is that important? Because when we perform a measurement, we need to choose a basis. So let's say for now, we stick to this basis, right? The 0 and the 1. If we do that, and I give you a general quantum state, then I express it in terms of the basis, like this, then the probability that you are in the quantum state psi and you measure 0 is the absolute value of alpha squared. And likewise, the probability that when you are in the quantum state psi and you measure 1 gives you beta squared. So, and these are the only predictions of quantum theory. If I give you a state like this, quantum theory doesn't tell you that this actually exists. It tells you that given this expression, you can compute the probabilities of getting what outcome or the other. Now, how does this work in practice? And we'll look at a specific example. Let's say our quantum state psi is 1 over square root of 2, 0, plus 1 over square root of 2, 1. First of all, we need to check if this is a valid quantum state. Valid quantum state is this. And if we square 1 over square root of 2 gives us 1/2. If we square 1 over square root of 2 gives us 1/2. 1/2 plus 1/2 gives us 1. So far, so good. So this is a valid quantum state. What are the probabilities? The probability that given this quantum state psi, I measure 0, it is alpha squared. So that's 1/2. The probability that given this quantum state, I measure 1, that's 1/2. They sum up to 1. But, okay, how does the experiment look like? The experiment looks like this. We start with the 0 state. This is something that is classical. So we say that if you start with one of these base states and you measure in that basis, this will always give you, you measure 0, it always gives you 0. If you start with 1 and you measure 1, it always gives you 1. There's no probabilities when you start with that. And now this, you start with 0 because on a quantum computer, on a simulator, this thing is easy to prepare. Just like it's part of the physics of the devices. Now, another operation that you can perform is Hadamard gate. So this is a matrix, for those who know what a matrix is. But then, at the outcome of this, we get exactly this state, psi. But we don't have access to psi. We don't have access to it. The only thing we have access to is a measurement device. And here, what we do is, we say we measure. And this is supposed to be like a meter, something that is measuring. But you need to choose a basis. So this is given a basis. And we pick already a basis. Okay, so let's say I start with this one. I apply this operation. That gives me a quantum state that I don't have access to. I measure it. It can give me either 0 or 1. I measure it. Let's say it gives me 0. But then I redo the exact same experiment. I start with the 0 state. I apply the same operation. I obtain some quantum state that I don't have access to, which will be the same as in here. Mathematically, then I measure the same basis. In principle, like in classical physics, you expect that if you perform the exact same experiment, you get the exact same results. That's not the case. You could get 1. Then you repeat the experiment again. Let's say it gives you 1. Now you repeat it again. Let's say it gives you 1. Again, gives you 0. Again, gives you 0. Again, gives you 0. Now, if you perform the experiment these 7 times, you will see that the probability that you get 0 is 4 over 7. The probability that it gives you 1 is 3 over 7. It is not exactly 1/2, 1/2. But the more times you repeat the experiment, the closer you will get to 1/2, 1/2. Okay? And all right, so that's like the basics of like the theory behind it. Like here, like behind all of this, there's a formalism of the postulates of quantum mechanics. And the only thing that you can predict with those postulates is these probabilities. That in the experiment you produce by doing the same experiment many, many times and counting how much times you have one thing or the other. And it looks like a bummer that you do this exact same experiment, like everything is controlled, like people have tried to control this, like to control like everything that is behind on the experiment, and this thing happens all the time. You get different results after the same experiment. There's no one who can predict the result of one single quantum experiment. You need to redo the experiment many times, count how many times you get what, compute probabilities, and that's what you can predict. So it's like, now I'll start getting metaphysical, but it's like there's something that is keeping track of what you measured, right? Because let's say here, so I perform the experiment, right? And it gives me 0. I perform it again, it gives me 0. But the math is telling me that there should be a tendency for these two to become equal after a while, after I perform experiments. So there's something that it looks like there's something that is keeping track of what I get, so that in the future, it will equalize the probabilities. What is that? Who's keeping track of this? That's my question for you.
Well, isn't that one of those things where it's like overall it averages out, but at every single instant you wouldn't have a higher probability of 1 because you have more? Like right there, you have 2 zeros checked. If you run the experiment, there's no higher probability that you will get a 1 because you have 2 zeros, right? Like it is a 50-50, right?
Yeah, each experiment is independent of the previous one. Right? I could have done the same experiment 2 times and get 2 times 1.
Yeah, but like you pose the question, what makes it sort of average out? But I mean, if it's just random, that doesn't sound like there's like a guiding force that's leading it to being stable. It's just a random distribution, right?
Yeah, but there's also the question, like, when do I decide to stop the experiment? Do I stop after 2 times, after 10 times, after 1 million times? Because if I decide to stop this at 2 tries, then I see that probability of getting 0 is 100%. Probability of getting 1 is 0%.
But it's not actually. That's just your guess, right?
Exactly. Yeah.
Okay.
So when you perform the experiment, is you decide to stop, and that's your best guess so far of this thing.
Now, this is like, I thought when like a qubit was measured that's entangled, if I'm using the right terminology, that you would know that its entangled partner was going to be the opposite. If it was spin up, the other one was going to be spin down or something like that. But it sounds like, is this a different thing? Because it seems here you're not saying that any thing can be known about something that's entangled across, the universe, only a probability of what the next measurement can be.
Yes, it's something like that. And my hope is that we can do it more precise later, because entanglement is a property of 2 or more quantum systems. Here, we only have 1.
Oh, okay.
This
So
is
this is
just
not
one
entanglement yet.
qubit. Yeah. This
Right.
illustrates one of the things, which is superposition. So this thing here is a superposition. And if you want to get more technical, this is a superposition of 0 and 1. But yeah, entanglement is very interesting. We'll go there.
For sure.
Right now, we have enough to discuss if this. So there's this question that I always had, like, what's keeping track of this, right?
Mm-hmm.
In my mind, like, one of the first things I thought was, okay, I'm doing the experiment, and God is taking care of what He gives me. Like, when I do the experiment and I measure, I'm asking God, okay, tell me what is the outcome here. He gives me 1. Then I do the experiment and I ask Him again. He gives me something else. But behind the curtain, what God is doing is this math. And He's looking at these probabilities and He's saying, okay, I already gave you 0. Now I'm going to give you 0 again. But the next time I may give you 1. Right? Who decides? I know that's God's will. Right? But
I don't understand though what you mean by keeping track of it though, because like if you roll a dice in standard physics, you know, you roll it once, you get a 6, you roll it another time, you get a different number. If the dice isn't weighted and you roll it a bunch of times just because of the randomness of it, you're going to see sort of an equal 1/6 distribution of each of the numbers. And so like when you say that it's keeping track of it, it doesn't sound like a correct formulation to me because and like I'm not I don't know anything about quantum physics. But it's why I'm like just saying my understanding of what you're saying because like in classical physics wouldn't it be true to say that nobody's keeping track of the number that leads to this sort of equaling of all the numbers being equally chosen? It's just the fact that they're randomly chosen that they approach an equal.
Yeah, I see what you mean. Yeah, because like let's change the qubit for a coin. Like I'm
Yeah,
throwing a coin and there's nothing behind keeping track of how many times it gives me heads, how many times sorry, how many times it gives me another thing. Because like at the end, if it's not balanced, like you said, it will still converge to 50-50.
right.
Okay. Okay, that I think that's a fair argument. But yeah, okay, maybe maybe it's not that clear here. Maybe yeah, I guess if you go okay, I'll come back to this when we see entanglement because like entanglement is really completely different than superposition. But yeah, you're right.
Okay.
Like in this case, I can just change the qubit for a coin and
Yeah.
it right like the probabilities balance out without no one keeping track of this.
Okay.
Yeah, I'll revisit this when we look at entanglement. Okay.
Okay.
Okay. So that's one thing. The other thing is, what is that? Right?
Psi, is that the psi symbol?
Yeah, this psi, this superposition, this quantum state. What is this? This is a vector. Okay.
Right.
But it's a vector where? Right? Because we're saying the qubit is either 0 or 1. When I measure it, it gives me 0 or 1. It never gives me 0 and 1 at the same time. Right?
Right. So it's a superposition of those two different
Yes. Yeah.
okay.
And this is like all that is here. That's the whole reason why people like when a physicist try to speak about superposition, for instance, he says things like, and I'll do it like together with you. Like, look at this. This is 0 and 1 at the same time, right? But it's not that. It's
Right.
not that. It's math, right? But of course, if I'm speaking to the public about this, I'm not going to teach them the math right away. But I'm going to lose them like after 5 minutes. But if they stick to this and I'm able to write it down, then I can say this is a superposition. It's not 0 and 1 at the same time. It's, formally speaking, a linear combination of these two basis states. But
Yeah, that's cool.
but now, like, where is this? Is this in the universe? Or is it information about my uncertainty about what the measurement is going to give me? Because,
Well, I
yeah,
got
go
something to
ahead.
say about that. When it comes to math in relation to theoretical physics, isn't isn't it the correct formulation to say that math is not actually saying anything about the mechanics of how, like, what is the substance itself actually? It's just a description of the observation of those substances in time. And so, like, if this is the example I've said is like if you throw a ball, the parabolic equation that would describe its movement with gravity and such isn't it isn't like that equation is baked into the ball. It's just that's like our mathematical description of what we're seeing, right?
Yes. Okay, let's say we do that. Let's go there. And I'll just keep this right here. Let's say you're here and you throw a ball and it does a parabola, right? This thing, so this will be given by a force that you put when you throw it out. There's also gravity pulling it down. So there's a vector of direction. There's a force that you put into the ball. There's gravity that is pulling it down, and there's no wind and things like that. But that's what drives this, like whole mechanics, right? Also, like the ball has a mass m, and there's an equation that I don't remember, but there's an equation that tells you, like, if this is the floor, that tells you where it's going to land and when, right?
Right.
There's no uncertainty there, right? And at every moment in time, let's say, for example, here, if I make how do you say, like coordinates here, I know that at this moment in time, I'm at position x that depends on the time t, and position y of t. If I change the time, it's going to move like either this way or that way. Now, these two positions that the equations give me. If I solve the equations, it will give me the exact positions depending on time.
So, but the question you asked was about basically, if I know the terms right, the pilot wave theory. So like you have, a probability that's happening. The question you're asking is like, is there a pilot sort of deciding under the structure reality what those conclusions are?
The pilot wave theory is an interpretation of quantum mechanics.
Right.
Now, quantum mechanics is this. I do the calculations and I do the experiment. The counts approximate the probabilities. The more experiments, the more times you repeat the experiment. Interpretations is, what is this?
Right.
The pilot wave is saying something like, so this is like the simplest form of a wave function. Now it's a wave because it can be like on these superpositions between 0 and 1, but here is like discrete. Like when you think about a wave, it's more like continuous, right? Let's say let's say the board is made of water and I throw a rock into it, it will make like ripples, like this. What the pilot wave is saying is there is a wave in the universe. We don't have access to it. We've never seen it before, but it is there. We have no way of how to even detect it, right? And how does the wave behave? Like this. And what particles or qubits are doing is you're throwing the particle here and the wave is driving it somewhere. So the particle itself has a trajectory, well-defined trajectory. And at some point, when you look at it, it turns out it's here. So it's like 0, for example. But then you do that again, you throw the particle here in the same place, but now, because there's like the wave moves like in all directions, it may end up here, right? But you threw it in exactly the same place, right? But you need this wave that you don't know if it exists. You need this wave to exist for this setup to be right.
Right. Now, so the original question you asked was more like before the pilot wave theory, well, is there a good theory that we should use? I guess like the sum of my thoughts of that, I think this is like sort of the final conclusion of my thoughts is like, I think we equally don't know. So like, we don't know if there is a pilot wave or like what is making, if it's actually random or if there's actually something happening underneath it or like what that function is. But equally, I would say about standard physics, like we don't know what even gravity is. So you have G there pulling it down, but we don't know like what that is necessarily. Now in like general relativity, like it's explained a bit for sure, but and I'm speaking like way out of my leagues here, just basically what other people have said, but they've said that quantum and and relatively don't combine totally. And so like my feeling is that like really when it comes to everything, including standard physics, like yes, we have good descriptions of it. Like we know what the function of gravity is. It pulls down, but we don't really know the essence of that. And so like that seems similar to like the quantum physics, where like we know that it's going to be equally one or the other, but that's the description of it. We don't know really what it is. Like we know gravity pulls things down, but we don't know what it is.
Yeah, no, I agree. The thing
Okay.
is, okay, before going to general relativity, we can touch on that. I have some good things to say about that. But let's say we come to this setup, right? Like we've all seen this in high school, right? We know there's some equations that you solve, it gives you this. We throw a ball, it follows this trajectory. Now, what do we say when we solve this type of equations? We say that this is the state of the system. What does that mean? That means that I have something that completely determines my system. Okay? So I know, like, for instance, like the height. Now I know implicitly the constant for gravity. I know the force that I threw it with in the direction that I threw it. So that gives me everything I need to know about the system, right? The problem is that when we start talking about quantum mechanics, we say that the state of the system is this.
Right. Yeah.
Okay. We call this also like the state vector. But we always say like the state, just like we do here. But the problem is, once I have the state in classical physics, I know everything there is to know. I can predict where it's going to be and when, but not here.
And so that's where that confusion comes, where the physicists will say that it's both true and false, because that's the state. But that's a different kind of idea of state than classical physics.
Yeah, exactly. And like you can even see this, like let's say you're on an atom, right? And you have an electron. And electrons have energy levels. Let's say one of those energy levels is this zero state. But what is an energy level on an atom? It's like is where the electron is like likely to be found, right? Let's say this is like a shell. And this one is another level. So it's like, I don't know, like a flower like this. So what does this mean? If the electron is doing this, if this is the state of the electron,
right?
Where is the electron? Is it in both places at the same time? Right? That's the thing. Like, we don't know. When we measure the electron, it gives us, okay, now it's here. So I know it was on this state. But if it was here, then I know it's on this like big, small shell. Right? But before doing the measurement, if I want to predict, and the only thing I can predict is probabilities, I need to do the math as if the electron is doing this.
Right.
So it's like, and this, again, this is what we call a wave function. So it's like the electrons or the particles or quantum systems, they behave as particles when we look at them. But when you're not looking, they behave like waves. How? We don't know. Like, it could be like the electron itself becomes a wave, or it could be that there's a pilot wave. That depends on your interpretation of quantum mechanics.
Right. That's where Jacob Baranda's idea was to get rid of the idea of space as being this continuous thing where an object has to like travel all the moments, and he thought about it as stochastic frames, where like the measurement causes maybe a frame to exist. I'm not sure exactly how that happens in his model, but then you know, so for him, then the problem seems to go away because it's not like you're thinking of the the particle or the electron or whatever as like, you know, specifically traveling to location, but it's like, you know, almost jumping across space or something. I don't know.
Yes, let's say. Yeah, I think he touches on this for the double-slit experiment. Maybe that's something we can do because double-slit experiment is not about entanglement; it's about superposition. Okay, let's do that. Yeah, I'll try to keep this. Or no, maybe not. I want the space. Now, the double-slit experiment is important because it helps you, like, this thing with qubits 0 and 1 is like maybe too abstract. What does 0 mean? What does 1 mean? But the double-slit experiment lets you like pinpoint it, like say, okay, it is here or is it there? Right? It's more like tangible.
And it was the first like experiment they did where they actually figured out this was happening, right?
I don't remember if it's this one or the Stern-Gerlach experiment.
Okay.
The Stern-Gerlach is for spins. So,
okay.
And the spin is a qubit mathematically. So the same thing I did here that's also the math of spins. But yeah, we can go to that one. That one is also interesting because you can try to think for the Stern-Gerlach. There's some processes that you do that if you try to think about it, because at some point, like you throw something and you put a barrier, and you will try to think, okay, this is a filter. Like if I only have two outcomes and I block one, right? But if you think about it like it's wrong. So you have to think about it like quantum mechanically. So we can go there, but let's go for the double-slit experiment first. Let's say I have a gun here, and it throws electrons or photons. It throws them in this direction, and here I have a big screen, and here I put one slit. What happens if I throw balls here? Well, some of them are going to pass like completely like in this direction, but some of them can pass like with a bit of an angle, like to be able to go across this. So here I will see something like this. Something like a Gaussian distribution. And how do I get this? Well, I throw it one, then I get one hit. Throw it again, I get one hit here. Throw it again, another hit there. Throw it again, hit here, hit here, hit there, hit here, hit here, hit here. So it's this graph is like a frequency of how many hits I get. Okay? And throwing one electron is one experiment. I need to redo the experiment many, many times. If I do this a lot of times, then here I see like a Gaussian distribution, like a bell curve. Does that. Now, what happens if I have here two slits? But instead of throwing an electron, I'm going to throw a wave. So let's say the board is made of water, and I throw a rock here. Now, you start going to see ripples. And what happens when the ripples get here? The ripples will like go through these two, but it will produce two again. So it will produce one here and one there. And they will start propagating. And at some point, like these new ones are going to start like intersecting. These intersections is what we call interference, right? So when you throw like two rocks, you will see like there's some ripples in the water, and the pattern is not going to be like uniform as when you throw one. When you throw one, you're going to see just ripples. But when you throw, like there's places in which like they will come together and the weight will be like a little bit higher. And there's another places in which like the part that goes down will come together, and they will come like completely like down even more. So all this process, that's what we call interference. And interference happens whenever you have waves, right? You don't need quantum for this to happen. And you continue on doing this. And now this like detection screen, what it will detect is like how hard the wave hits. Okay, like the force of the wave. So
I am familiar with this one. So this is the one where then it produces that like, interference pattern on the walls.
yes. Yeah. But the important thing is I am aligning this thing. Let's look at this line. This line is imaginary. This is just for me and you. This line does not exist in the experiment. This line goes directly into this thing that is a barrier. Okay, nothing can go like through this because there's only two slits here and there, just here and there. But when you look at the force that is produced here, the highest force is here, right behind this line, right where this line hits. So right behind this barrier. All right. So, and now you have other things here, like this. And this actually goes to 0. Okay, so maybe I should use another color there. Let's say all right, so this is like the force of the waves hitting the screen. The highest force is behind the barrier. Why? Because of interference. And this you obtain it by writing down the wave equations here, evolving the waves all the way to the end, and seeing where the wave is highest, where the wave is like, this is basically the height of the weight of the wave when it hits the screen. So far, so good?
Yeah. I'm familiar with this. Yeah.
Okay, cool.
I know this.
Now, we do the same thing with electrons. Now, the thing with electrons is that we don't know what they're doing. And we throw one at a time. Okay? Now, I'm going to leave this here, and I'm going to throw now electrons. I have my electron gun. Let's be dramatic. And I throw one electron. If you think about the electron as a particle, it will never hit here. Right? Because if you throw a ball, like a rock, it will hit there and it will not pass. But you throw one and it hits here. You throw another one, it's here. You throw another one, it's here. Another one, there. Another one, another one. And the vast majority of the electrons that you throw hit there.
Right.
Now, you don't know what is happening between the moment in which you throw the electron and the moment in which you detect it here. You don't know what is happening here because you're not looking there.
The internet?
Yeah, as I was saying, so you throw the electron, you don't know what is happening here until it hits the detection screen. You do this many times.
And
yes.
Right. And so I'm familiar. So here, what they did is when they throw the particle, they observe that it acts like a wave. It can land in places where it couldn't if it was just a solid particle. But then when they measure it right before it goes through the slits, they see that it's acting like a particle, like it has a specific location that wouldn't allow it actually to.
Yeah, exactly. It wouldn't allow it to go like through both slits, right? A wave goes through both slits, right? Because it hits both slits and it propagates after the slits, right? And after the slits is now two waves that can interfere among them. But
So this is where they're saying that it's both, you know, true and false because it's going through two things. It feels like it has, it doesn't just seem like it's a probability. It feels like it's doing both simultaneously.
yeah, exactly. Yeah. So look, let's say I'm with the first electron that I throw. With the first one. I throw the first electron, right? And let's try to keep track of it. Now, it should go here. If it goes like in this line, it will hit here and it will do nothing. Nothing like on the detection screen. It could go like a little bit off, like in this direction and hit there.
Mm-hmm.
It could go like in the other direction and hit there. And that's what you will expect to see. You will expect to see like something like here and something like here. And that's it. Nothing on this yellow line. Right? You will expect the electrons to hit here and there only. But they do hit where the yellow line is. But this only happens for waves that we know of. If instead of throwing an electron, I throw a wave, then I see this wave here, it propagates here, and now this wave these two waves interfere. And it's going to give you the highest intensity there. And that's where the electron hits with the highest probability. But what this means is, or is not what this means. It's like, I'm trying to like explain it. So is it that as soon as I throw the electron and I'm not looking at it, it becomes a wave. It hits the double slit as a wave. It comes out of it as two waves or as a superposition of two waves. Then these two waves interfere among each other. But the electron is these two waves. So the electron is interfering with itself. This interference of the waves, that's the electron doing it to itself. And here at the end, it hits the screen as a particle. So the wave comes all the way to the detection screen, and there's a wave. How does the wave look like? It looks like this blue one. But then the electron needs to decide, where do I hit? So it needs to like become a wave. Once I throw it, behave as a wave, and when it's going to be detected, it needs to say, okay, I'm about to be detected, so I better choose a place to land. How do I choose that? I compute probability, apparently.
Yeah.
Yeah, and like this arises like when you're able to like throw like individual electrons, right? If you throw many, then you can say, okay, some of the electrons are going this way and they're like colliding with each other. So after this, there's a mess of collisions, and that's why you see this, maybe, right? But when you start throwing like single electrons, it's like, what is happening?
Right. It's a very, very, very strange phenomena.
Very disturbing. So because it's again, like only when I'm not looking at it, because now you can do something else. Now you can say, okay, let's put a detector in one of the slits. Let's say I put an electron detector here. Okay, let me redo this thing. Now, what is this doing? This is going to, like, if there's an electron here, it's going to light up, and I'll be able to see that this detection was, this detector gave me a detection of an electron there. So I know that if the electron is detected here, the electron is there as a particle, right? If I don't see a detection here, that means the electron is here as a particle, because it only has two ways of going through the slits, either here or there. Now, what happens if you do this? You throw the electron. Let's say I got it on the detection here, at this detector behind the screen. Sorry, behind the double slit. So here, it stops behaving as a wave because I detected it. I detected it, it is a particle. And from now on, it goes and it is here. I throw another electron. It's not detected here. So it becomes a particle there. Because if I don't detect it here, then it is here. There's only two possibilities. So it goes and it hits there. I throw another electron there, another one there, there. And now I see these curves. If I was throwing single particles, rocks, balls, you see? They're going through one of the slits. Now, why? Because at this moment, I'm forcing the electron to be a particle, not a wave. Because that's it. So when you measure the electron, it's always measured as a particle, never as a wave. So if I detect it here, at this moment, it becomes a particle. If it was a wave before, right? I don't know if it was a wave before or if there's a pilot wave, but at this moment, I'm forcing it. I'm saying, okay, tell me where you are. That's what this detection is doing, is asking this question to the electron. And if the electron answers, it's going to say, I'm either here or there. That's particle information.
Mm-hmm.
A wave cannot answer that question. And that's the strange thing, right? It looks like, if you approach this like naively, is like the electron has a will, I guess. Because like the electron is designed, oh, okay, so you're going to detect me here, so I'm going to behave as a particle now. If you don't detect me, then I can do whatever I want. I'm going to be a wave.
Right. And it's not just that there's some kind of interference happening with the particle, because on the other side, like, what if you had 3 slits and you only measured one of them? You would still then see it go through as a particle.
Yeah.
Because, like, just the possibility that it could have been measured, even though it wasn't measured, turns it into a, is that true? It turns it into a particle again?
Yeah. So you have to be careful when you start adding slits, because let's do that. Let's say I add a third one, right? And I redo the experiment. But I put only one detector, right? Like there.
Mm-hmm.
If I detect it here, then it is a particle and it's going to hit there. If I don't detect it here, I don't know which one it went through. So now the electron, when it's not detected here, it has the freedom of behaving as a wave in the other two slits. So behind these two, you will see interferences, but not behind this one. You see, so it's about how much information you can get out of the quantum system.
Now, when you're talking about something being observed, so classically, when something is observed, it feels like the thing that's being observed shouldn't be affected by the fact it's being observed.
Yes.
But since we're talking about electrons, these are photons. Aren't these like photons or something? So
yeah, either. Yeah, let's say they're electrons or photons. Mm-hmm.
So like, to be observed doesn't seem innocuous to me, because it doesn't, it like, because it's like the basic unit of matter.
Mm-hmm.
To be observed, it has to be like what, like touched by a sensing mechanism, right?
Yes.
Or something. So it is kind of like colliding with something. It's not like like you know, a bear passing through the woods where when it's being observed, nothing's colliding with it. Only light is emitting off of it.
Mhm.
This is the actual unit of light that's being emitted. So it's not like this thing can emit things that allow it to be detected from a distance. It itself has to collide with something.
Yeah. So there's like this like this paper that they used to use for photographs. It's like photosensitive.
Right.
So what you can do is you put one of those things like very large, and then you put, let's say, one slit just to try to start with the experiment, right? So this is like the photosensitive like plate or like a sheet. But now here you have, let's say, a flashlight, right? If you're too close and you turn on the flashlight, then you're going to see like a lot of hits, right?
Mm-hmm.
But then what people found out is, I think it's, yeah, I don't remember what they used, but what you can do is you start getting away, start getting away, start getting away. And now instead of like just leaving the lamp, the flashlight, just like that, you just like turn it on and off right away, right? And you get like farther and farther away. Now at some point when you do that, on this like plate, you will see 1 point. That's one photon hit.
Mm-hmm.
For electrons, what you do is you detect charge. So you have this thing will be connected to a very sensitive mechanism. Everything is completely isolated. That you put when you calibrate this thing, you see that there's no electric current there, but the electron has charge. So if there's an electron hitting there, then you will measure some electric change. That's your electron hit.
This is maybe going to sound like a dumb question. So you're saying the photon and the electron are different when you're measuring charge. The other,
Yeah.
but what is the actual electron? I thought it was a like light. Like what in the like
Oh, so the electron is a particle that has negative charge. Okay, and that's the unit, the smallest unit of electric charge.
it's so like what kind of particle you're talking like so it's pre like matter, right? Like it's not like it's a substance like a piece of wood. It's like it's not like an element or anything. It's like that's why I thought it was light because
Yeah, exactly. So, okay, let's go down there. So when you look at let's say the periodic table, like the one at the top left, that's hydrogen. It is there because it's the simplest of them all. So hydrogen, and it has some numbers like one there. It's atomic number. That means the atom has one proton and one electron. Now, a proton has positive charge and a mass, mp. I don't remember. It's a very small number. How you measure these things? I have no idea. Have to look at that. The electron has negative charge, and it has some units, like, but this is like the basic unit of electric charge. So this is like the negative one, and this is a positive. Why they're called positive and negative? That's a convention. Like you can redo all of that. Like changing these two, it will change nothing. Like only but the labels. And this one has another mass, mp, the mass of the electron. And what happens is you put them together and they're like stay together. Now, you could say, what happens in electromagnetism? Let's say this is a particle and the electron is a particle. Why am I going to say they're particles? Because when you detect them, they are particles, right? So let's stick to that. Let's stick to, these are particles, but because when I detect them, they're like in just one place. So you have proton there and electron there. And I'm exaggerating the size. The electron is way much smaller. Oh, and they also have like a size. But let's stick to this. Now that's the electron, the hydrogen atom. One proton, one electron. But there's also like electromagnetism. Electromagnetism tells you like equal charges, they attract. But opposite charges, no, sorry, equal charges repel. So if I have like a positive and a positive, there will be a force that is pushing them apart. But if you have a minus and a plus, there are forces trying to bring them together. Why is that not happening here? Right? The electron is never like arbitrarily close to the proton. And when you start going to other atoms, like you will have now, like for helium, you'll have two protons and then maybe neutrons, and then two electrons somewhere. But this is still positively charged, and these are negative. They should go there. And this was like a big question when quantum mechanics started, like, what is happening here? And instead of that, like they stay around the nucleus instead of like falling back. And the answer is quantum mechanics. So you have to write down like the equations, Schrodinger equation, plug in all of these values, all of these variables, solve Schrodinger equation, and it gives you exactly what you see when you measure an atom. Right? So it's very, very complicated, but there's things like seem to be violated here, but it actually comes to like the loss of quantum physics. So yeah, so the electrons are here. Now, what mediates this interaction? These are photons. So you think about this like if this is a positive charge and this is a positive charge, the photon, let's say I'm going to put it blue. This one has no charge, but it interacts with charged particles. So meaning that if there's a positive charge and there's a positive charge, there will be electrons. There will be photons like going in these directions, like between one and the other, making this repulsion, forcing these particles to like go away. But in this case, the photons will do something different. Like here, the photons will like go that way and go that way. So if it's like this proton is like throwing something that way, so it starts moving like back because it threw something. So now all the other way. And the same thing for this one. So like the photon is a mediator. Photon is light. And photons have no mass. So the mass of the photon is exactly 0. Does that answer the question?
Yeah, definitely.
Okay.
Now I'm going to interject. This is just a different topic. Want to just get your feeling about this. So the video quality, make sure it's good, or are you just kind of like, well, let's just do it? Or
no, let's go with it.
Just go with it? Okay.
Yeah.
All right.
Yeah. Okay. Now, where were we before this?
So yeah, we were talking about the double-slit experiments.
Oh yeah. Mm-hmm.
And
yeah, the double-slit. Yeah, exactly. So yeah, the double-slit works if you throw photons, particles of light, if you throw electrons, if you throw protons, if you throw like even like atoms, whole atoms, it still works exactly as I said. And I think that the biggest thing that they throw is a big molecule, big in terms of these sizes.
Yeah.
That's like it's like a ball made by carbon atoms.
Really?
You heard of this before?
No.
So it's I'm very bad at drawing, but it becomes like it's a three-dimensional thing that has some regular shapes in the links between the carbons. But these are each corner is a carbon atom. Carbon is I don't remember if it's 6, 8, 12, but it's the atomic number. So it has many protons, many photons, many protons, many electrons, like each one of these, each corner. And these are like many, like forming a ball. And you throw these things on the double-slit experiment, and you get exactly the same behavior.
Wow.
Yeah, and that's one of the things, like where does this behavior breaks, right? Like how big can you go?
Could it just be that there there is like no necessary place where it breaks? It's just that the bigger you get, the more chance you have that it's going to collide with something else, and what is it called? Lose its coherence or whatever.
Yeah. Yes, that's another interesting thing that you touch, because in order for quantum mechanical behavior to like emerge on your experiments, you need to isolate your experiment from the rest of the universe. For example, in the double-slit experiment, I was drawing, you have a cannon here, and you throw something, and there's a double slit here, and there's a detection screen. You need to actually do it like this. You need to put a hard wall, like, because why? Because there could be that there's a gamma ray coming from the sun, very energetic, and it goes here and it hits your electron when it's right there, and that counts as a measurement apparently, and it messes up your interference. Or it could be that you have another photon coming from somewhere else, and now it hits the screen, and it messes up your pattern, right? And you control this how? Well, you plug in cables very carefully. Right?
What's the difference between the interaction between the carbon molecule and its other components, and an interaction between that carbon molecule and the observer? Because the observer causes it to decoherence or whatever the term is, but the molecule itself has like internal maybe collisions, or maybe it's not. But like, I'm wondering, so like, if it is the case that the state collapses, that's the right term, the state collapses when it's measured, that's like, I'm thinking about in terms of the state collapses when it has an interaction with something else. But like, the carbon atom itself is like almost touching its own elements, and so like it has what, electrons and stuff like this, and so then it's a molecule with maybe electrons and protons, and then when it collides with another molecule with electrons and protons, then the state collapses, but its own electrons and protons aren't enough to collapse its own state.
Apparently not. So let's say that you're throwing like this big ball of many carbon atoms, like linked. You throw one of these things. Let's say something like that. Now you throw it there, and okay, I think I understand now what you're saying. So this ball is supposed to be stable, right? So it's not supposed, like, because like they done like experiments like individually just for this thing, like just put it on a vacuum and leave it there, and then observe if like the electrons go away or not, or like what happens to this. So these are like stable, like, and when they hit here, they still have that form, like all of the electrons, all of the energy that corresponds to that molecule, like it's still there when it hits the screen. Like all of this has to be like really carefully calibrated. Yeah, I don't know the details, but that's what you need to do if you want to observe quantum behavior. Yeah, and what else can I say here? So here, okay, maybe I can go also like to quantum computers. So in quantum computers, this thing about the isolation. So a quantum computer has these qubits, but they need to be superconducting temperatures. Now, superconducting temperatures is like very close to zero. There's like a quantum computer, like a superconducting quantum computer. When it is turned on, it is one of the coldest places in the universe. Now, for many things. So a quantum computer looks like this. Maybe I'll draw it bigger. Something like this. Then there's a big wall. Now, what is this? These are like special plates and like cables going down. And this is supposed to be closed. And now here, again, you plug in cables very carefully, a lot of cables, because you need to control many, many things. Now you have a vacuum pump. You put this into a vacuum. So you need a vacuum. You also need to cool it down. So it needs to be cold. Once you do that, and again, it's one of the coldest places in the universe, if not the coldest place in the universe. And all of that is to make work a tiny dot there at the bottom. That's the quantum system. All of the rest is for this thing to behave as a quantum system. So you're isolating, like from the universe, this thing. So this is a big fridge, like you like close it completely. You put it on a vacuum because you don't want other particles to interact with your quantum system. If that happens, then you lose your like quantumness there. Because it looks like it becomes you said decoherence, right? So your quantum state like degrades. It becomes classical state. It stops being quantum. So you remove all the particles from it, and then you cool it down. Why? Because heat is energy, and energy interacts with quantum systems. That's why you need to cool it down, but also at a specific threshold of temperature is when you start having superconductivity. Superconductivity is a quantum effect. And that happens when you, on this specific type of material and how you produce it, when you cool it down below a certain point. But if you like make it superconducting, then it's still not working because there's too much energy in the system and it messes up your quantum behavior. So you need to cool it down even more to reduce the amount of energy that interacts with your quantum system. So what you're doing here is you're isolating your quantum system from the rest of the universe. If you don't do that, you don't have quantum effects.
What's the math of superconductivity? Like, what is that? You say that was a quantum thing?
Yes, superconductivity. It's actually we use a specific type of property called quantum tunneling. So, and I think, yeah, okay, yeah, we can do that. So the math is complicated, but I can make some analogies with what we've been doing. Now, the easiest way of explaining superconductivity is this. Let's say you take a cable. Like this. Now, these are two cables that are not touching each other. And then I put here something that does not allow a current to pass through there. So for instance, let's say I have a light bulb like connected to this. And I plug in here a battery. This is my intent of a battery. And I pass current. The light bulb will not light. Okay? If I remove this and I plug in and I plug the cables, then that will close the circuit and I can turn on the light bulb.
Mm-hmm.
Okay? That's conductivity, right? What is superconductivity? You make this, actually I know a little bit more of the details. So aluminum is a conducting material. You can conduct electricity through aluminum, but not through aluminum oxide. So you build this with aluminum, then you oxidate a little bit of it, and then you keep on putting aluminum. This is how these actual qubits are built. So in like specific chambers. So now there's another thing that we know about aluminum is that it becomes superconducting when you cool it down, like close to the absolute zero. What that means is now it's not going to be a light bulb. It's going to be something else that detects like the current that is going there. So you plug in like your detectors that are like somewhere. When you cool it down and you pass a current, you will now see a signal. But this needs to be really, really cold. Now, and the signal is different because when you do electricity, like very naively, electricity is electrons going in one direction or the other. So electrons moving, that's electricity. In this case, it's not single electrons. So, and you have to solve like a quantum mechanical system, but what's happening is you see electrons like on this side, like on this part of the aluminum, coupling between them. Now, these are two negative particles, right? Negative particles, they have equal charge, they should like repel. Now, they're coupling in the sense that when they move together. But there's no positive particles like for them to like attach to. So let's say like when they move, now you see them here, like at the same distance. And this happens because of superconductivity. These are called Cooper pairs. And they become quantum mechanical systems, which means you can try to understand them as if they were waves. All right? But this wave is a little bit different than what we saw on the double-slit experiment, because in the double-slit experiment, like the wave like moves through space, right? But the wave function that we're gonna look here is energy of the system. And in a graph, let's say I plot like this direction. I'm gonna try to make a plot of what's happening here. And there I have my barrier. And on this axis, I'm gonna plot energy. The energy of the system, the energy of one Cooper pair. So these two electrons that move together. It turns out that if you throw like just one electron, then its energy looks like this, right? So it doesn't have enough energy to go through the barrier. It will bounce back. That's when the material is not superconducting. When the material is superconducting, the energy of the system is higher. So when it moves here, it's gonna hit this part. So now I'm gonna draw it like this. So this part, like this wave is going to move there, and it's going to hit this part. When it hits it, it's going to decrease rapidly than it did before. And here is not that dramatic, so I'll probably redo it. It's going to be like this, and then like this. But at the end, it's going to pass as something that is non-zero. But remember, in quantum mechanics, we have probabilities. What this is quantifying is a probability. So this is the probability that the Cooper pair moves to the other side of this barrier that doesn't allow for to conduct electricity. That's quantum tunneling. Quantum tunneling is you have a non-zero probability that your particles can be in the other side.
Very interesting. Is it possible that that happens because, and this may be a very, very ignorant question, but like thinking about the way that the double-slit experiment worked, is it possible that the particle, you know, is acting like a wave and the barrier is like stopping like 90% of the paths it could take, but then there's like one little path it could take that like it just sneaks through? Because like, what is the barrier actually? Is it like a bunch of like molecules? You're saying it was like a specific maybe copper or something that was non-conductive or something. So like when the electron moves towards the barrier, it's like a bunch of particles. Is it just like, you know, the wave function of it like sort of like distributes out and then it has a chance of finding a way through? Is that possible?
Yeah, exactly like that. Yeah, that's exactly what I was trying to picture here. Like, so it hits the barrier here, but once it's there, it's saying, okay, I'm not being detected. I'm allowed to behave as a wave. And if I were a wave, I can also be on that side.
Mm-hmm.
And it's good.
Yeah.
Yeah.
But I'm just like that's the math of it. Though I'm saying like mechanically, like what exactly is that that uh conductor, the blue thing on the chalkboard there? Because like I'm thinking of like, so if the conductor is like a bunch of like trees in a forest, because they're like molecules, so each molecule that's a part of the insulator, rather, the insulator is a bunch of trees, and then you're basically, it's like is then it possible that the electron is like somebody firing a bullet, and you know they fire it many times and it may hit the individual trees, but then there's a slight chance that it'll go through. Because like what you're describing is like, okay, you're describing it on a more abstract term. You have like the insulator, and you have the quantum wave, and then it has a probability of going through it. I'm just asking I'm like trying to connect the dots between the double-slit experiment. Like, is it the same thing where it's like it's trying to find a path through it? Like,
yeah, that is a Nobel Prize winning question. If you answer that, I assure you, you get a Nobel Prize. Nobody knows. Yeah, that's the issue. Like, this is the only thing that the only thing we can do about this is math. I cannot tell you what is happening there. I can only compute probabilities.
Very cool.
Yeah. Intriguing. Okay, let's do Stern-Gerlach experiment. Or do you have any other things about this?
I'm fascinated. Yeah, just keep going.
Okay, cool. Glad you like it. Now, the Stern-Gerlach experiment is, I'll start with the setup. So you had an oven. It's an oven. And you put, I think it was silver. Now, why silver? Because like they understood the atomic structure of silver, and they know that it has many, many electrons, but in the outer shell, there was only one electron, not coupled to others, because there are like energy levels in which you can have 2 electrons or 8 or 5, but silver was easy to find, and it had like just one electron at the outer shell. So effectively, it's like throwing electrons, right? Later on, this was refined. Like now that we have more technology, we can do it directly with electrons, and it happens exactly the same way. So, and now what you do is, from this oven, you throw them, and they build a specific type of magnetic field. So let's say, usually, let's say I put 2 magnets. One is like the positive side, and one is the negative side, or the north and the south pole for electric. For magnets. This will create a magnetic field that is something like this, like parallel. And this is like a uniform magnetic field. That's not what they did. What they did is to bend this a little bit. Instead, they did this. They put like a wedge here, and then this one was flat. And what happened is that now the magnetic field goes like this in the middle, but on the outer sides, it curves. Something like that. Now, this is facing us, right? And they say, okay, now this is the C direction, because it's like going up, right? Usually when we talk about like coordinates, we say, okay, up and down is the C direction. So let's stick to that. So this is one apparatus that is aligned on the C direction. And we're looking at it like this. But what we actually want is, we want to throw the silver atoms in this direction. Okay, like through this point here. There. So this thing, like I need to like rotate it in this way and plug it like next to the oven. So if I do that, now I'm just gonna throw the apparatus like this. And this is an apparatus on this C direction, right? And now I throw these atoms. Now, I would like to draw the path of this thing. I'm not gonna do that, because we know, because we've been talking about this, that it's gonna behave in a very different way than if I draw a path. And then they put detection string. So this thing will pass through this magnetic field. And this thing is charged because it's like an electron. An electron is charged. They were expecting to measure like through many of this, and at the end, measure something like this. Because like some of the electrons will not get deviated, they will go on a straight line and hit right there. Some of them will be deviated a little bit up, some of them will be deviated a little bit down. So you will see like some hits like distributed along this the C direction, like up and down. But that's not what happens. What happens is you see only 2 places with hits. You see hits either here or there. And if you draw the line, they never hit in the middle. Now, what they say is, well, not them like, and not in the original paper, like how we understand it now, is we say, okay, the electrons or the silver atoms that are here in this place, I'm gonna call them spin up, right? And I'm gonna draw this notation again, the one with the cats, but with a different symbol. Instead of a 0 or a 1, I'm gonna draw like these arrows. So this is going to be up state. And the one below is going to be down. Okay? And that's how they come up with the names, right? So this one is hitting up, this one is hitting down, this is the spin up, this is a spin down. Now, but we know that spins are qubits. So this is going to be the 1, 0 vector, and this is going to be the 0, 1 vector. All right. It turns out that all of this thing right before the detection screen is building this state psi that is going to be 1 over square root of 2 up plus 1 over square root of 2 down. So here at the end, this is the state of the system. This is the wave function. And what happens when it hits? It has to decide on one of these two. And we know you have 50% probabilities of being measured up, 50% probabilities of being measured down. Okay, just as we were doing with qubits. But now what? Now, this thing was aligned along the C direction. So if I look at it like this, so we had this, and it had like the magnetic field like that, and this was the C direction, right? Like along the C direction. But what I can do, because I'm throwing like particles like in this way, in this direction. So what I can do is twist it like this, right? So now I will have something that is like this. And I have the magnetic field now twisted too. And I call this an apparatus, but now in the Y direction. Okay, because now this will correspond to the Y-axis when we do physics and coordinates, we call this the Y-axis. So the labels are like completely arbitrary. It's just like to give a name. So this is one direction, this is another direction. And let's do now this experiment. All right. Let's say now I throw this and I put the apparatus, but now in the Y direction. What happens in the screen? Same thing. I only get hits in two places. But now it's like a different direction, right? Before it was like up and down. Now this is going to be like right and left. So we're going to call this like the right state. And this is going to be like the left state. And effectively, all this process is building a quantum state that is right over square root of 2 plus 1 over square root of 2 left. Okay, so far so good, right?
Yep.
Now let's complicate this. Let's make it much more interesting. Let's say I plug in first the C in the C direction. And I throw my electrons, my silver atoms. I know it's going to hit in either one of two places, up or down, right? So instead of putting like a whole detection screen, I'm just going to put it in the place where the down state will hit. For example, I'm going to do this. So I know, like, because I can measure like the separation and all of that, that everything that hits here is going to be on the down state. So if I have something that is not hitting there, I know it is on the up state. This is a little bit like the double-slit experiment. You see that? So because I have information of which way it is going. So if it is up, it's going to go like in this direction. But I'm not hitting it with anything. And I can pass it again to another C apparatus. So let's say like that. Okay, so here I am filtering the up and down state. The down state is going to be always detected there. If it's not detected there, that means it's up. And I'm going to pass that to another experiment in the C direction. What do I see at the end? In this case, there's nothing weird happening. You only see the up state. Right? You only see hits here in the up state. Okay, that makes sense. It's okay. This thing is a filter, right? And I'm filtering the down state. Same thing happens if I put here Y and Y, right? I put it on the Y, I block like the left direction. I only let pass the right direction. Then I pass it to the Y experiment again, and I only see the up direction. So it looks like a filter, right? But what happens if I change the second one? So in my setup, I'm passing electrons through here. They can be up and down after the detection. If they get detected here, they're down. If they're not, they're up. So this will be always up if something goes like through here. Now I'm plugging in a Y apparatus. What do I see? What do you think I will see in the detection screen? Now remember, after the Y, you could see left or right. After the C, you see up or down.
Yeah, maybe like half, maybe it's like quarter, like maybe it's like in between up and down, like because you have before you had like two directions,
Yes.
and then now you have these two. Is it like a combination so that it's like maybe it's like halfway in between the like?
Yeah, that's a good classical intuition. I agree. That's what you will think. What happens is this. You see hits here, both on right and on the left. And the probabilities is 50% of the electrons that you throw, they end up here on the first barrier. That's 50%. And here you see 25% and 25%. Again, you have to throw many, and you converge to these probabilities. These probabilities, you compute them with quantum mechanics.
So it's like the splitting it between the z-axis and only having up particles go through doesn't affect at all the y-axis. It like they're still entirely left and right or whatever.
Yeah.
Basically.
Yeah. Now, how do we do this quantum mechanically? We have everything we know. We have everything we need to understand what this is happening. Look. So at this point, like I know that if something is detected here, is down, right? If it's not, it's up. And I pass it through this thing, and I have 0 probabilities of not being measured left or right. Like this thing, when it's here, is going to be measured either left or right. It has no other possibility because I pass it through a Y experiment. So what I'm saying is that this up state, I can write it down in terms of the right and the left states. So this will be some value that I don't remember. It has complex numbers in it, so I'm not going to put them. So this will be some alpha, right, plus beta left. And it turns out that alpha squared gives you 1/2. and beta squared gives you 1/2. And this is the probability that you measure right, and this is the probability that you measure left. And this is what happens. But these are probabilities of everything that passed through the first detection screen. So this is 50% of what passed through here, but only passes 50% of the times, because this one is already a filter.
Right.
Right? So that's why you get here 50%, and the other 50% goes here, and it splits into two, into right and left, each one with half that probability. So that's why you have here 50%, and here you have 25% and 25%. All right? But this is the important thing. The up state is related to the right state and the left state. These two are also vectors in the same space. Which space? I don't know. We call it the Hilbert space. So this space of vectors is what, when you hear a physicist talking, that's Hilbert space, the space of these vectors. And they're related in that space, right? Not in the universe, like not here, like not like I cannot touch this thing. It's somewhere else. And this is what determines these probabilities. Now, we can go even deeper than this. Okay, let's stick to the same story. I do C apparatus, and I filter everything that is down. So everything that is down will hit here. I only pass things that are up. I do the same thing. Now I pass it to the Y apparatus. Everything that was up passes to the right, to the Y apparatus. But now this one has right and left. I'm gonna block one of those. Which one? It turns out it doesn't matter. So I'm just gonna choose one. Here it also doesn't matter. Like I could have covered the up and then pass it down, and everything works in exactly the same way. So here I'm gonna block the left state. So if something passes through here, it's gonna be the up state. If something passes through here, it's gonna be the right state. Now what do? I plug in another C apparatus. So this will be another C apparatus. And this is where the magic begins. Look, let's try to think about it as filters, right? So far, our interpretation was this thing is filtering up and down. It's letting pass only the things that are up and is blocking things that are down. Okay, this worked when we put C and then the C. We never see the down because it works as a filter, apparently. But if I throw one electron, let's say I throw only one, right? It has two possibilities. Either hits the screen here or it passes. If it passes, it's on the up state. Because everything that is down, it's hitting here. It's staying there. Now pass it through here. Now I'm letting pass everything that is right. I'm blocking everything that is left. And I get to the last one. And here I'm going to measure. But after a C, I can see up and down. But if I think about this as filters, this is filtering the down state. I should never be able to see the down state there, but I see it. So it's not a filter. So here you do measure up and down with specific probabilities. Now the numbers will become more complicated in this case, but it's a non-zero probability. So we have some probability of hitting something here, some probability of hitting something here, and two equal probabilities, small, of hitting something here. I think it's not that complicated. I think it's 50% here, then 25% here, and then half of that, 13, 12.5. So what is happening? Am I filtering the down state or not? Wasn't the down state staying there?
Yeah, I mean, like, I guess I don't know enough about what the down state is for like for it to seem that paradoxical to me, because like in classical physics, if you like maybe take a board and you cut, you know, a stick, or you cut like a slit and you throw a stick at it, and it maybe, or maybe it's like, you know, something which maybe makes the stick like converge to being up or down, right? So then it like the stick's thrown this way, it like kind of like rights it and it goes through. And then you do that again with the other direction, you wouldn't expect it to maintain its filteredness. You would expect it to get filtered to this and then to that. So like I don't understand necessarily why it's expected that it would keep its spin. Like if something like spinning is a specific thing. Like if you have a spinning object that's like spinning like this, and then you rotate it like this, and then you hit it through another thing, it could like spin to the other direction.
That's very good classical intuition.
Right.
The spin is not that. It's not like there's something spinning. Actually, there was a calculation. So they compute like the number of the spin, and if you try to think about it like the electron like spinning, and you know like the electron is not exactly a point. It has like a dimension. So if you think about the electron as a particle, and I'm gonna like zoom in like this. Let's say this is our electron, and you convert like the numbers of this spin to rotation, then this thing will be like rotating. You compute that velocity, that rotational velocity. So like the outer shell of the electron would be moving faster than light. And that's apparently impossible, right? So it's not like the electron is spinning. That's how people explain it. Why? Because they don't want to get into the math of this. What is actually happening, well, not how we understand it, is this. At this moment in time, I have a superposition of up and down. I have 1 over square root of 2 up plus 1 over square root of 2 down. And this is like the last postulate that I haven't talked about, which is the collapse postulate. So at this moment, let's say I throw one of those. If it hits the screen, I know the electron is down. So it's not anymore this superposition. It becomes instantaneously the down state. The collapse is this becomes this instantaneously. There's no delay between the two. Now, in the postulates of quantum mechanics, this is done as an update rule. This is just mathematics that they say, okay, I'm going to treat my quantum system as this. When it is detected, I just update my state. I forget about this one because it's not this one anymore. It is this one now. Okay, so I do that. If it gets detected down, then I know it's down. If it doesn't get detected down, then that means it is up, because there's no other possibility. So it is up. But now what? Now I pass it through this thing. But we know that up state is related to the right and the left states by some numbers. Now, same thing. Now, this is the state at this moment in time, but now it has to be detected. So it is forced to be either right or left. If it gets detected left, that means it was hit here on the screen. If it doesn't hit this screen, then it is right. So that's like at this moment, it will be the right state. But now, the right state after passing to this apparatus, you can write it down now as up and down states. So this will be something like, I don't know, it will be like x up plus y, no, not x and y, other letters, alpha, beta, gamma, delta. So this will be gamma, delta, down. And again, this is just something that happens on the Hilbert space. This is an equation, right? I can write down this vector as this. And what happens is that now this gives me the probability that this is detected as up. And this gives me the probability that it gets detected as down. Now, if I do the math here, then gamma squared is 50%. And delta squared is 50%. But it's 50-50 of what is left after this. So on the first one, I have 50% probabilities because my state is this. So it's 50% probabilities is up, 50% probabilities is down. So I get 50% of hits in the down state. 50% of the times it will pass. Now I have this state. Now alpha squared is 50%, beta squared is 50%. From those 50% that happened. So I will have half that. It's 25% here, 25% there. Now I pass that through here. And what is left is 50% up, 50% down. But what is left is 25%. So that will be half of that on each. And this is how we understand this. This is called a sequential Stern-Gerlach experiment, not as filters. If you think about it as filters, the state down should never be there. But if you do the math, you get non-zero probabilities. And you get the exact probabilities. Like this way of computing probabilities is the, how do you say it? Is the most accurate formula that humans have come about. The formula of computing probabilities is the thing that has like many digits of precision, like after the decimal point. Not in this setting, like in this setting is good, but it's in measuring other things of particles. And you have no other place in science that has that level of accuracy. Was it confusing enough?
I think I understand it. I mean, it doesn't seem, again, it doesn't seem too paradoxical or counterintuitive that it can reset its ability to have a spin up and spin down state when it goes through the Y thing. But that's basically what you're saying, is that when it goes through the Z thing, it gets a polarity of either up or down. Then when it goes through the Y thing, it gets a polarity of either left or right. And then when it goes through the Z thing again, it's not like it filtered out the possibility to go down. It still has the possibility to be filtered. You're saying it's not a filter, but like it still has the possibility to be have a polarity of up and down again.
Yeah, exactly.
Yeah, that makes sense. Yeah.
Yeah, so that's Stern-Gerlach. And all of this is just superposition and like the postulates of quantum mechanics. Now, so the postulates is the state of a physical system is a wave function. It's a vector on a Hilbert space. That's the first postulate. The second postulate is that when you measure what we call a matrix, specific type of matrix. They call it a Hermitian matrix. So it needs to satisfy some mathematical properties. And from that matrix, you measure what is called eigenvalues. And that is what corresponds to here, like state up, state down, state right, step left, and the up and down. All this can be formalized in that language. And here I'm just trying to avoid all of that so that we stand like in the ground. Now, another postulate is the Schrödinger equation. Now, Schrödinger equation is differential equation that involves vectors and matrices and complex numbers. So, and it tells you like how the state vector, how the state of a system evolves in time when it is a wave. Now, that may be something interesting to look at, because look this, check this out. So as I was saying, the wave function, the state of the system, of the quantum system, lives on a Hilbert space, whatever that is. It's a space of vectors. But these vectors don't mean anything there, because like vectors in real life, they can tell you like directions and magnitudes. So if you throw a ball, a rock, then the magnitude of it is like the velocity, sorry, the direction. No, wait. So, okay, so if I stay here and I throw a rock again, then a vector here means, so the length of this vector is like the force that I put on it. The direction of the vector is where I threw it. So this vector has like a physical grounding, right? But yeah, what is this vector? And that's even worse, because this alpha and beta, like this is a vector and it has real numbers in it, right? It has like the force and the direction in each one of the axes. That's okay. But these are complex numbers. This doesn't make sense. Like there are no complex numbers in this universe. We only measure real things. So where is this in the universe? We don't know. But let's look at Schrödinger's equation. Schrödinger's equation is I h bar. Maybe I'll do it bigger because this is important. It's I h bar sine of t. Now I'm getting out of space. I h bar sine of t. This is a ket. Ah, man. I'm lacking the derivative. So this is the derivative with respect to time of sine t is equal to h sine 0. And there's a hat here in this h. Now, what does this mean? This is the initial state of the system. It's like when I throw an electron, like I know its position, I know its energy because it's me who's throwing it, right? So I know the state of the electron at that moment in time. That's the initial state of the experiment. This is initial state. There's a derivative here, apparently. This tells me how the state evolves in time. So this is like the future and the past of my system. And I have two constants there. Let me get another color. Okay, so what are my constants? Is this thing, this is the reduced Planck constant. This is something that we can measure, like with experiments. And we also have an I. What is I? I is the complex constant. So I is the square root of -1. Now, this thing doesn't make sense, because square root is something that you square and it gives you that number, but nothing squared gives you -1. So what we did is we say, okay, we're just going to give it a name and treat it as if it is a number that when you square it, it gives you -1. So that's what this I means. So now you have I, this thing, we call it the imaginary unit, and Planck's constant. Then the future and the past of your system, the initial state, and this thing. This H is called the Hamiltonian. That's the total energy of your system. All right. Now, what is the total energy? That's basically kinetic energy plus potential energy. So kinetic energy is anything that comes from the mass of the thing and its movement. And the potential energy is if there's like something else, like an electromagnetic field or something like that is interacting also with the system. So you have to plug all of that into this H. Now, largely, what the Schrödinger equation is saying is you have two constants here. So these are like fixed numbers. They don't change with time. This thing changes with time, right? And the Hamiltonian can also change with time. That's okay. But what he's saying is up to a constant, the future and the past of the system depends only on your initial state and the energy of the system. You see that?
The future and past of the system only depends on the initial state and the energy.
Yes. And the future depends on the energy.
The future and the past, but isn't the initial state the... Oh, so like, yeah, you have the initial state and then you have the past and the future. But wait, I thought in quantum physics, the state was like uncertain, I guess, but it's a probability. So it's like, I mean,
yeah, so
I mean,
that's the thing. So here, there are no probabilities. This is just a differential equation on a Hilbert space with complex numbers. This tells you how the quantum state evolves. The evolution of the quantum state, which could be a superposition, and we don't know if the superposition exists in reality, like in this universe or not, then the evolution of that depends only on the energy. Now, let me rephrase it. This H bar is in the universe, right? We measure it here in the universe. This H, the total energy, we measure it here in the universe. This is in the universe. This, we don't know if it's in the universe. This initial state is in the universe. It's something that I can, like, I'm sure it's there. So this side of the equation is in the universe. This side of the equation, I don't know if it's in the universe. I don't know if this, like in the future, this could be a superposition. But I'm like putting it equal to something that is in the universe. And this H bar, again, is in the universe. I can pass it through the other side and leave only the I here. Let's do that. So I'm going to put this over H bar, and I'm going to remove this here. So now I have things that are in the universe equal to things that I don't know if they're in the universe. That's a very strange equation.
I think I kind of intuitively understand it. Wait, is it something analogous to basically like when you are working with quantum systems and stuff, like you measure, stuff that's in reality, but then maybe if the photon continues after you've measured it, so the initial state is the starting state, which is on the on the right. But then if it continues, then it would end up in the other position where maybe it's here or maybe it's there. So like, is the state that's not in the universe, is that the quantum state, like the, either spin up or spin down, and then this state is like knowing its measurement is spin up?
Yeah. So let's say here you have something that is spin up. You know it is spin up because you filter it, right? Then you do evolution, right? You will need to account for all the forces acting on your system. Then you apply that on there. That tells you how it's going to behave in the future.
Mm-hmm.
With some I there.
But when you say how it's going to behave in the future, that is like, well, it's either going to be this or this, like a probability type thing, maybe.
Yeah, exactly.
Okay.
Probability type of thing that you compute from the wave function.
Right.
This is the wave function. And the derivative is basically telling you how the wave function changes with time. That's like a grosso modo what the derivative is.
Okay. Yeah. I think I do intuitively understand it.
Mm-hmm.
Like, I don't necessarily know what all the components of this exactly are, but I get the gist of it.
Yeah, exactly. Yeah, no, we will need way much more time to get into the details, but this thing can be done like for example, in Stern-Gerlach experiment, that's a very easy and intuitive way of understanding what's happening quantum mechanically, and how to break this idea of thinking about it classically, like as if they were filters. Like that's not working.
Right.
And in those kind of systems, then you can write this thing and solve it, but it requires more time,
Yeah.
But yeah, so I found this, and actually this of putting the Schrodinger equation in this way. I just did it like in the last couple of days. Like I was thinking about this because I'm having an intern here at my job, and I have some free time for the intern. So I tell, okay, we're gonna read some philosophical physics, right? Because I was actually listening to the Jacob, and I got the first paper about that, and it's talking about this. It's like trying to see if the quantum state is real or not. Is it ontic or is it epistemic? It's ontic if it's actually here in the universe, and it's epistemic if it only helps me compute probabilities.
Mm.
Right? And it gets really into the details. So then I thought, okay, but Schrodinger's equation is not mentioned in the paper. But if I write it down like this, then this thing is in the universe. This thing is ontic. And this thing is epistemic. Right? And it comes from the best scientific theory that we have. So what do I do with this? I mean, probably somebody else noticed this before. I'm not claiming this is mine, but just find it really bizarre. What do you think?
I mean, I don't understand it enough to interface with that proposition.
Yeah, no.
Like you're yeah, I mean, I understand the intuition of the epistemic and ontic, because what you're saying is that when you have a quantum system, what is actually happening behind this, like we were saying, the pilot wave, what's actually happening? We're maybe using math to describe it, but that's not necessarily exactly what it is. It maybe is just a description or our way of describing it. I understand that intuition, but when it comes to this equation and how you were writing, so it sounds like you wrote this down in a way of basically making Jacob Brandis's formulations work with your understanding of quantum physics, but I don't understand this well enough to know how that connected the dots or anything.
Okay. No, that's okay. We can fix that if you invite me again. What I can do is try to develop I'll try to do this on my own, and when I get something like a more specific example in which we can map this. You see?
Right. Yeah,
So
yeah.
that you understand it. And now I can tell you, now this side of the equation is ontic. The other side is epistemic. What is
Right.
happening, right?
That'd be cool.
I'll need to look for like and to work out like one example completely.
Yeah, that'd be really cool.
Yeah, for sure. Okay. You want to move to entanglement?
Sure. Yeah.
Okay. Now all of this is okay, but entanglement is really weird. So all of this is just warm up for entanglement. Now, and there's one subtlety about entanglement. Let's say I have the postulates of quantum mechanics. The system is described, the first postulate is the system is described by a state vector, or this like wave function. So I'm gonna run this C, a cat. It's a vector in a Hilbert space. Now, two, I have an observable. An observable is a mathematical object. It's a matrix. It's a matrix. A that I'm gonna draw with a hat. So that's usually what you do with observables. You put a hat so that you know when you write it down that it's an observable. And let's say this is just a table A, B, C, D. With some properties stick to these numbers. Three is the outcomes of the experiment are linked to this matrix. So outcomes of experiments are properties of A. Now, for those who know about matrices, these are eigenvalues, right? But it's just some information that you can get from this matrix, not directly A, B, C, and D, but something that you can obtain with A, B, C, and D. So outcomes of the experiments are properties of this matrix A. And you have to like fix this, like every time you do an experiment. So the A may be different for spins than for the double slit experiment. So you have to change it. The state is also different. It may be like a bigger vector, like for spins is two-dimensional. It has two entries, the vector. For the double slit experiment, it has infinitely many. It's infinite size. Anyway, now for the probabilities, you can compute probabilities that when you start in a specific state, you obtain one of the things that are linked to this A. So these are the probabilities of the measurement outcomes on your experiment. So I'm going to call this, let's say, alpha. No, I already used alpha. I'm running out of letters. Let's say X. And this is like for all the possible X, there are eigenvalues of this A, whatever that means. Phi is Schrödinger's equation. So I, H bar, derivative with respect to time of the state is equal to H hat of psi 0. This tells you how your system evolves in time. No, that's good if you're working only with one particle. If you work with more than one particles, you need another postulate. Postulate number 6. If psi describes a system and I have one system, let's say one particle, one spin is psi, and I have another one, let's say phi, describes another system. Then the joint system is described by another mathematical operation that many people don't know. It's called a tensor product. And we write it down like this. Now, I'm going to do this explicitly for spins, right? And what should be like strange about this is that why isn't it just a pair, right? If I have one particle here and another there, like why isn't like the joint state like just the pair? Why do I need that tensor there? And nobody knows, right? This is just what makes the math work. If you plug it there, then again you have this description of probabilities that gives you the most accurate formulas that we have access to. So that's just how nature works, apparently. Okay, now let's move into that, because now, if you forget about physics completely, and I give you just these things, these are axioms on a mathematical theory, right? Axiom 1, I'm going to work with vectors on a Hilbert space. Axiom 2, I'm going to work with matrices with specific properties. Axiom 3 is they're going to have specific values that I care about. Axiom 4, I can obtain this by doing some kind of dot experiment with some probabilities that I can compute. I'm going to have a differential equation that defines how this evolves in time. And if I have more than one system, I just need to do tensor products between them. So I give you those axioms. Now, this lives on Platonic space, right? I don't need the universe for these axioms. Inside Platonic space, I can mathematically prove there is a thing that I call entanglement. In other words, entanglement is a mathematical consequence of the postulates of quantum mechanics.
Yeah, I mean, that seems pretty natural.
Yeah, it does. And there are many things in quantum mechanics that are like that. For example, Heisenberg's uncertainty principle. Like you hear this like all over the place. If you put a podcast, a discussion on YouTube on quantum mechanics, 90% of the times you hear Heisenberg's uncertainty principle. They say, this is something that is in nature, that it's there. Heisenberg's uncertainty principle is a theorem that you can prove from these axioms. Like you can forget about the universe. You buy these axioms, you prove Heisenberg's uncertainty principle, and it's true in the universe.
I would, but I mean, how is that not trivial though? Because the math is like describing something. So like if if we go back to the parabolic arc of a ball thing, if you have the axioms that you have gravity, which is going to pull down on the ball, this, and then you give it a force of this, you then can conclude that it's going to go in this specific direction, in Platonic space. How is that? Is that like the same analogy?
Well, I can say, okay, you throw a ball, right? Now, gravity is in the universe, right? You don't need anything for that. Like the vector that determines like the velocity and the direction of where you throw the rock, the ball, that's also in the universe. There's no magic about it. The equation that links all of this to where it's going to land, that is not in the universe. Right?
Right.
Right. And I can solve that equation without knowing the equation. And that's what like the baseball players do, right? Because like if I hit the ball and there's a fielder, down in the field, and he solves the equation, right? He gets the ball.
Yeah.
Intuitively, right? But the equation is not in the universe. He doesn't even need to think about the equation.
Okay.
It's on Platonic space.
Yeah, that makes sense. I was just making sure that I am tracking that is the same kind of idea.
Yeah, it's exactly the same kind of idea. Yeah.
Okay.
All right, so now crash course on tensor products. If you start with a vector AB and you do a tensor product with another vector CD, there's a formula for this. Now, this is what we need for to define like this tensor product for spins. Now, we will do that with spins, so that's why I'm sticking to two-dimensional vectors. The formula is this: AC, AD, BC, BD. Okay? That's a tensor product. I start with one thing that is two-dimensional, one thing that is two-dimensional, and I end up with something that is four-dimensional. So even at this moment, like at this level of the easiest type of wave functions, I end up with something that is four-dimensional. So this, like, the dimension like explodes. And every spin that you add increases this exponentially.
Yep, makes sense.
Yeah, so it becomes like really, really complicated. And another thing is, like, we are used to thinking that x times y is equal to y times x. That when you multiply things, they're like commutative. Like the order of the factors does not affect the product. Right? This thing is not like that. Look, if I do CD tensor AB, this is CA. Now I'm gonna put them in the right order. C. Now CB, I'm gonna put BC. Now VA is gonna be AD. DB is gonna be BD. Now the first two are equal, but not the two in the middle, right? So it is not true that the order in the tensor product does not matter. Here, the order matters. So that's like the first thing to notice about the tensor product. Now, another thing, like before doing tensor products, we did this thing with the bases. So we started with this vector 1, 0 and 0, 1. And these two are special because if I do another vector, say alpha, beta, this I can always write it down as these vectors. So this will be alpha 1, 0 plus beta 0, 1. So these vectors that have like one in only one place are special, right? And now I can take that property and put it here in these four-dimensional vectors. So let's say I do that. Now in 4 dimensions, I can have this vector 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. And now every vector in these 4 dimensions, I can write it down in terms of these ones. So for instance, if I take alpha, beta, gamma, and delta, this becomes alpha 1, 0, 0, 0 plus beta 0, 1, 0, 0 plus gamma 0, 0, 1, 0 plus delta 0, 0, 0, 1. All right. Now that's cool, but we can do something else. So that's in 4 dimensions. But we started with things that were 2-dimensional. So let's tensor product the basis from the 2-dimension. So what I'm saying is, let's take this one and make a tensor product with itself. What is this? This gives me 1 times 1 is 1. 1 times 0, 0. 0 times 1, 0. 0 times 0, 0. Aha, is the first one. Now, 1, 0, tensor product, 0, 1. 1 times 0 is 0. 1 times 1 is 1. 0 times 0 is 0. 0 times 1 is 0. Is the second one. Right? And that happens with all the others. So now I have 0, 1, tensor 1, 0. This will give me 0 times 1 is 0. 0 times 0, 0. 1 times 1 is 1. 1 times 0 is 0. That's the third one here. And finally, 0, 1, tensor 0, 1. This will be 0 times 0, 0. 0 times 1, 0. 1 times 0, 0. 1 times 1 is 1. And that's the last one. So what that means is that with the basis vectors, this 1, 0, and 0, 1, I can produce this one in 4 dimensions by just doing tensor products between them. Okay. And now, and once I have these 4, I know I can decompose like any 4-dimensional vector in terms of these 4. All right, now what? Now, we have these 4 vectors. Any other vector here is a combination of these 4, like the one I just erased. So let's say alpha, beta, gamma, delta is alpha 1, 0, 0, 0 plus beta 0, 1, 0, 0 plus gamma 0, 0, 1, 0 plus delta 0, 0, 0, 1. But now let's come back to physics, right? So all of this was just math. Now in physics, I have a superposition state. If I have a spin, it can be up and down, right? But it can also be a superposition between the two. So let's say my first state is like this. Is x up, and remember that the up is this one, right? The 1, 0 plus y, some other number, down. And the down is this one, 0, 1. So as a vector, this will be x, y. And now I have another state, right, from other spin. So this phi, let's say. This one will have other numbers there. This will be c up plus w down. So as a vector is c double. And I want to form the tensor product of these two. And how you think about this is, okay, your first state, this state psi, it determines like the state of your spin. And in general, it can be doing a superposition of these things. So I'm going to do this plus y down. So that's my first spin. What is my second spin? Is c up plus w down. The 6th postulate of quantum mechanics. It says the joint system has as a state the tensor product of these two. What is that? Well, this behaves as a product when you perform this type of operations. So what you will have is, and it's non-commutative, right? So what you will have is x times c, and these are just numbers. You multiply them as numbers. And the up and the up, I'm going to let them express. So I'm going to put them like this. Now, this is just a symbol. This means something. And what it means is this. So here, let me erase this. This is up times up. This is up. Tensor product up. And this thing, I'm also going to write it like this. So this symbol means I'm doing a tensor product, and I'm just not denoting the tensor product. This is what people do. So it can be confusing. But what it means is I'm doing this tensor product. Now, for the other one, x times w. I have up and down. Up and down. Same thing. This is the tensor product of the up with the down. And it is actually like this vector here. Now the next one will be this one times this. So this will be yc down up. And notice, like this is up down and this is down up. I cannot mix these two, but they are different. And finally, I have yw down down. Now, what is this? This thing is a four-dimensional vector that I obtain by doing a tensor product of two superpositions of spins. So far, so good?
Yeah, I think so.
Okay. Cool. Now, what is happening mathematically on the tensor product of vectors? Look at this thing. This part here, this is just any four-dimensional vector, right? Any four-dimensional vector looks like this. I can choose alpha, beta, gamma, and delta, however I want. But like you have to respect like this, and that's what I'm going to do. Okay. And the state that I'm going to choose is a very simple state to write down. Is 1 over square root of 2 up plus 1 over square root of 2 down down. Now you can see that this one squared plus this one squared gives me 1. So this will give me a probability distribution. And this is a valid four-dimensional quantum state. But here, what did I do? Like, what is this? This thing is, this represents all the possible four-dimensional vectors that I can write down when I do tensor products of superpositions. What is a tensor product of superpositions? This is the most general thing that one spin can be doing, a superposition with some variables x and y that have some conditions. And this is the most general thing that the other spin can be doing. And I'm putting them together, forming a four-dimensional vector in this four-dimensional space. And I get this thing. Now, can I get this state to be of this form? So the question is, what happens if I equate this to that? Meaning, can I have two superpositions that when I plug them in with this tensor product gives me this state? This state is possible because I have a four-dimensional space. This is a viable, like real, not real, but this is a viable state of the system because I'm on a tensor product. What are the equations? the equations is up, 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 up. So this number has to be this number. So I have 1 over square root of 2 should be equal to x times c. First equation. Now this one, x times w, will be on up and down, but there's no up and down. So this needs to be 0. You see that?
Wait. So the big equation on the bottom is the tensor product of the two states. But then what is this other one that you're trying to equate it with on the top?
Yeah, that's actually because I'm trying to not say entanglement. So in this case, so you have 2 superpositions, and then you expand everything, right? And it gives you this expression.
Right.
Right? Okay, now, forget about this, you understand this. When you're on this 4-dimensional space, now this 4-dimensional space is where like systems of 2 spins live, right? Because that's the postulate. The postulate says, form all the tensor products, it gives you a 4-dimensional vector, right? So, and this thing is a 4-dimensional vector. But these are all the 4-dimensional vectors that I can form via tensor products of superpositions.
Right. So that one basically is like all the possibilities. It's this one is spin up, this one's spin down, this one's spin up, this one's spin down. Is that right?
Yeah. Yeah, exactly. So this one can be up or down or a superposition. The other one is up or down or a superposition. All these possibilities are encoded in this expression.
Got it. Yeah.
But I'm working on a 4-dimensional space. Okay. And in that 4-dimensional space, I can write down this. This is a 4-dimensional valid vector, mathematically. Okay. So now what I want to see is, can I form this state with a tensor product like this?
Wait, now this one that you're writing down, the difference is that the one of the big one has all the possibilities. This one's defined. It has 2 up and 2 down, kind of.
Yes, but this gives you all the possibilities of what you can form with 2 superpositions. What I'm trying to show is that those are not all the possibilities in the 4-dimensional space. What I'm going to show is that this, you cannot form it like that. This is an entangled state. And I'm going to show you like exactly mathematically what entanglement is.
Okay.
Okay? So now what I'm trying to do is I'm going to equate this. This has like all the freedom of 2 superpositions, right? I can choose X, Y, C, and W as I want. They have to sum up to probabilities. But if I solve some equations and I find X, Y, C, and W, then I can write down this state as this vector, right? And it will be a tensor of 2 superpositions. I'm going to write the equations now. And I'm going to equate the values next to each one of the tensor products of the spins. So I have spin up, up here. I want to equate it with this, up, up. The number next to it is 1 over square root of 2. That's this. But here is x times c. Now, here I have xw on the up, down. But the up, down doesn't appear here. So that means that the value of this xw should be 0. So xw is 0. Now, the spin down, up does not appear here. So yc is 0. And yw is for down, down. That's 1 over square root of 2. This is 1 yw. Okay, so I reduced everything to these 4 equations. And coming back to this, if I'm able to find x, y, c, and w that solves these equations, then this state, I can write it down as a tensor product of superpositions. Like describing individually what state is one spin and what state is the other spin.
Mm-hmm.
Now, how do I solve this? Let me stick to this here. Okay, just to give me some space. Now let's solve this. And this is very simple because I have things equating to 0. So let's pick one of those. This one. X times W gives me 0. That means that either X is 0 or W is 0. So I have X is 0 or W is 0. Let's pick one specific case. Let's say X is equal to 0. Okay, if X is equal to 0, then I go and look at the other equation because I need to solve them all simultaneously. And this equation will say that 1 over square root of 2 is X times C, but X is equal to 0. But 0 times anything gives me 0. So I'm saying that 1 over square root of 2, which is not 0, is equal to 0. That's a contradiction. Okay, so that means that X cannot be 0, right? It better be that W is equal to 0 because X times W is 0. So W needs to be equal to 0. But now we go and look at another equation. This equation. This one means that 1 over square root of 2 is equal to Y. I don't know what Y is, but I know what W is. W needs to be 0. So I get 1 over square root of 2, which is not 0, is equal to 0. That's a logical contradiction. So what this proves is that the assumption that I made is false. The only assumption that I made is that I can equate this state, which is a tensor product of superpositions, to this state. And now, like overall, what this says is this thing cannot be described as by describing what one spin is doing and what the other spin is doing.
Mm-hmm.
Okay, so it's not a tensor product of two like independent systems.
Yep.
Okay, so that's entanglement, like by definition, when you cannot put one state in terms of tensor products of others. But there's more to it. So let's forget about the math for now. And let's come back to the physics. And I'm gonna leave that there. And as you see, like all of this is just math, right? I'm not invoking the universe here. All right. Now let's come back to the just one spin. When you have just one spin, let's say, and you have this state, this is telling you, like the number next to it, when you square it, gives you the probability that that state is being measured, right? So probability of measuring down is 1 over square root of 2 squared. So that's 1/2. So you have 50% probabilities of measuring down. If I give you another thing, let's say square root of 3 over 4 up plus square root of 1 over 4 down, then this means that measuring up has square root of 3 over 4 squared. That's 3/4. I have 3/4 probability of measuring up. And the probability of measuring down is square root of 1 over 4 squared. So that's 1 over 4. Right? So that's the probability of measuring down. So these numbers give me the probabilities of measuring this.
Question, you're saying
Yes.
it's the square root of like 1/4 squared. Where's the squared part coming in?
Oh, that's that's the law of that's one of the postulates of quantum mechanics. So if I give you this, I think it was the fourth that I wrote down. So the probability that my state is, so this is my state psi. Now my state psi is given by this, and I want to know the probability that I measure up. And what the rule says is also called the Born rule, if you heard it before. Is go to this expression, take the number that is next to the up state, and so that's the number, and then square it.
Okay.
That's the probability formula. Like you have to
Right.
buy it with all the other axioms.
Right, right.
And that gives you 3/4. Okay. Okay, so that's that. But what this means, so and this is in general, like not only for spins, but for any type of quantum system. In particular, for quantum systems of two spins. For instance, if I have spin up, and I have, let's say my value is alpha, beta, this will be up and down, gamma, down, up, delta, down, down. The probability of measuring, so let's say now this is my psi state, that was a 4-dimensional space. The probability that given this state psi is measured as down up is gamma squared. Okay? But with a subtlety. The subtlety is I have two systems to measure. Right? I have the system on the left and the system on the right. Right? I have like two spins. One, I have it here on my left hand, and the other one, I have it on my right hand. So the probability that when I measure both, it gives me the first one is down, the right one is up, is gamma squared. You see that? It doesn't matter if I measure one first or the other, or I can measure them both at the same time. That's okay, that's allowed. But I can only predict the probabilities.
So the probability that, what is gamma squared? Like,
okay, let's do a specific example. Let's say I have one over 2. Right? And I want the probability that given this state, I measure down up. Now, this quantum state tells me that the probability of measuring down up is, I need to go and look for the down up state. Is that one. I take the value that is next to it and I square it. That's 1/4. So 25% of the times, I'm gonna measure down up. And like all the others are equally likely, right? But I can also have things that are 0 in the state. So for instance, let's say I have this one and this one are 0. So let's say this one is 0 and this one is 0. And this one is 1 over square root of 2, 1 over square root of 2. Now, what's the probability that on psi I measure down up? Is the number that is next to it squared. So that's 0 squared, which is 0. Which means that if I'm on this state, if I prepare this state on my experiment, I will never measure down up.
Yep.
Okay? Now, what is the probability that on my state side I measure up, down? I look at my expression, is here, the up, down. Next to it is 1 over square root of 2. And then I square it. That's 1/2. So 50% of the times, I'm going to measure up, down. Okay?
Yep.
So same thing for up, same thing for down, down. Okay, so that's just the math. Now let's come back to the universe. What do these probabilities mean physically? You have a spin like on your left and a spin on your right. And you can decide when you measure one or the other, right? These are like final probabilities once you measure both of them. Now, what does this tells you? Look at this expression. Like these ones two are zero, so they will never come out as a result of experiments. But look at these two. These two have the left spin is up.
Mm-hmm.
So whenever I measure the left spin, it's always going to be measured as up.
Mm-hmm.
But when I measure the right spin, sometimes it's going to be up, sometimes it's going to be down. Right? And
Right.
with which probability? 50% this one, 50% that one. But that doesn't matter for the spin on the left. The spin on the left is always up.
Mm-hmm.
Right? When you measure it. All right. So this is a superposition. This is a superposition of up and down only for the spin on the right.
Right.
Okay. Actually, this state, you can write it down as a tensor product. So this will be up tensor product 1 over square root of 2 up plus 1 over square root of 2 down. Right? This is my first spin. It's always up. This is my second spin. It's on a superposition of up and down. So this system, I can describe it by telling you what's the state of the spin on the left and what's the state on the spin on the right. Is that correct?
Wait. I don't understand what you're doing on this one. Like, why are you doing the tensor product on the two things?
Oh, okay. Look. So here, I'm forgetting about this because they have zeros, right? So I'm just gonna erase them. And this is just one-dimensional, so I'm gonna erase this part too. Now here, I have this expression. This is again 4-dimensional vector on these tensor products of vectors. And I wrote it down like this. But here, this expression, what it actually means that I already erased, but it should be like up tensor product up plus 1 over square root of 2 up tensor product down. Okay, I'm just like plugging in the tensor product in between the two spins. That's this part here. And now you can see like this one on the left is the same, right? So, and let's say I just give you this state here. Up times up, that's a tensor product of these two. So that's this part. And I have 1 over square root of 2 as a factor. Right? Now plus this thing, so 1 over square root of 2, I plug it there. And then I have up tensor product down. That's up tensor product down. So here, I'm just doing math. I'm just manipulating the expression. Okay, so what I'm saying is that these three expressions are the same.
Mm-hmm.
Okay?
Oh, it's a manipulation thing. Okay, yeah.
Yeah, it's just a manipulation. Yeah, so I have the three things here described. But this one in the middle is a bit mysterious, right? Because I have like the implicit tensor product in between. It has only two factors. But this one, it shouldn't be that mysterious, because like this sixth postulate that I wrote is I give you one spin, I give you another, and then I do the tensor product. That's the joint space. So this is directly applying the sixth postulate. And I'm telling you, the first spin is always up. The second spin is on this superposition. So this last line, I can link is directly this postulate of the tensor products. But when I developed, it becomes this thing. Right? And they are the same thing.
Cool.
Okay, so far so good?
Yeah.
Okay, now, and again, like if I measure here like the spin on the left, it will always give me up, right? It doesn't matter the order in which I do it. Like if I first measure the one on the right, the one on the left is still going to give me always up, because the other probabilities are zeros. Now let's do this same thing for this state. We know that this state, we cannot write it down as a tensor product of two things. That's the equations that we were able to solve.
Right.
So now let's do that for this. Now, this thing, it has probabilities too. So what is the probability that this state, and I'm going to call psi again, that psi is measured as up and down? So up and down doesn't appear in the expression, so it must be zero. But that's also the probability that in this psi, I measure down, up. So these two, they don't come into play. I will never be able to measure these two. I can only measure up, up, and down, down. But now, let's do this. I have two spins, right? The one on the left and the one on the right. And I mix them up in a way that gives me this quantum state. This quantum state describes the joint system of the two after I did some interaction. And I give you one. And I take the other one. Now you go to the other side of the world and you measure your spin. What is it going to be? Well, according to this equation, you have 50% probability of measuring down and 50% probability of measuring up. Okay, so you don't know the result of your spin when you measure it. But let's say you measure it and it gives you, I don't know, up or down. Decide one.
Down.
Down. Okay, so you measure yours. Yours is the one on the right. Okay, so you get the down state. And you're very far away. What is the state of my spin? Look at this. So if you measure down and your qubit is the one on the right, sorry, your spin is the one on the right.
So yeah, it'll be up.
So you measure down.
Yeah.
Okay, so this is yours. That's yours. But mine has to be linked to the same quantum state.
Oh yeah, so it'd be down, right?
Okay, so it will be down. So mine is down because when you measured your spin and it gave you down, you know But the one
Right.
coupled to it has to be measured in the same direction.
Yep.
Right? Because of this mathematical expression. So you measure your state, you don't know what it's going to give you, but once you obtain the result, you know what my spin is going to be measured before I measure it. And you know this instantaneously.
Right.
Right? And this looks like you're sending information faster than light. But it's not. It's very, very subtle. And you need more math to be able to mathematically prove that this doesn't send information faster than light. The information that you send is meaningless. You cannot use that information for anything.
Mm.
Yeah, and this involves like information theory. Actually, there's a very cool algorithm, quantum algorithm, that shows this directly. It's quantum teleportation. But you need another formalism that describes also the quantum mechanics, which is the density matrix formalism, because it has like a specific type of operations that allows you to deal with these kind of things. So it's very, very subtle. It's hard to like pin down if you don't have like the precise language, but you cannot send information with this. It looks like you're sending information, but the thing that breaks it is that when you're about to measure your spin, you don't know what it's going to get.
Right.
And that's the subtlety. You only know after you measure the state.
Yeah. I mean, yeah, I've heard about that before, so I'm kind of familiar with that thing where it's more like when you measure your state, you find out about the other person's state, but in a way that isn't useful. But yeah.
Yeah. So, okay, so that's like the vanilla version of entanglement. These are just two systems. You can have 3, 4 systems, infinitely many systems entangled in an entangled state. So entangled state means you cannot write it down as a tensor product of individual states. And that's what a lot of things that involve quantum mechanics, like experiments, like take advantage of. So for instance, in quantum computing, so quantum algorithms, they're like one of their strengths is that they exploit quantum entanglement. So this thing is heavily used in quantum computing for abstract things.
Wait,
Yeah.
is the reason why it doesn't send information because when you entangle the state, it has to be like close? So you entangle the state like when it's close,
Yeah.
and then you move it far away and you measure it. It doesn't send information because it's, it would be the same thing as if you brought it close and then you already knew what it was and then you brought it far away, because it's like the information, you just didn't know about it.
Yes. Okay. Now, let me try to recreate that without quantum systems. Let's say I have gloves, right, for my hands. I have the left globe and the right globe. And you know that these are paired. One is left, one is left, one is right. And now I hide them in boxes. We both look away, and some other person gives us one to you and one to me. And we move far away. And now you open the box. And you know instantaneously which one I have. Right?
Right.
And same case for me. But this is, and for you, you have 50% probability of getting the right or the left globe, right? But the person who gives it to you, he knows which one he gives you.
Right.
And that is not happening in the quantum setting. So the correlation looks like this for you and me, but there needs to be somebody else that is deciding which one we're getting. Or we can put it like in a machine. Let's say we put it there and it scrambles them, and then I put the hand, I take one and I go away. Right? So this needs to be like something else that is making the decision of what we're taking. But in the quantum state, it's not like that. Like that probability, like that is still like a probability like on the air. Like it's a coin that is still flipping. And not until you open it, it becomes real. Like for the case of globes, once I take one, it becomes real. But not for the spins. So it's very subtle how this works. Yeah. And there's another thing about entanglement. So let's say now we're working with electrons, right? And each electron has a spin. And you have your electron here, and this is my electron. And they are brought together and put in this quantum state. Up, up, down, down. And now we take them apart. Very far away. Taking them apart does not, if you do it carefully, does not affect the quantum state. Like the distance between the electrons, once they are entangled, is not here. The distance doesn't come into play. Like not even time comes into play here. Because like the order in which we decide to measure the electrons, it doesn't matter.
Right.
So where is this? Like how do the electrons, they need to have access to this thing.
Yeah, I mean, I guess I know this isn't valid really, but you could suppose that they're already determined and that it's just not known yet.
Yeah. That's actually well, that's another like very, very subtle thing. But this some part of it is what they call hidden variables.
Right.
So a hidden variable would be, okay, there's something internal and private to the electrons, like at this moment in time, and they're sharing it. They say, okay, if you get measured down, and I'll get measured down too. Now they go apart, but this like treaty. Okay. So they already agreed what they're going to be measured. I don't remember the subtlety, but there's a theorem under certain assumptions that some of them involves like a free will, the other one is, I think it's Markovianity, something strange like that. But you need to put like extra assumptions, and then you can prove that there is an experiment that you can run, and depending on the results of the experiment, then you know if there are hidden variables or not. This is called Bell's theorem. And what he proves is that under these assumptions, there are no such thing as hidden variables.
Right.
This experiment satisfies those assumptions. So we know that from the beginning, they cannot be sharing a variable. They cannot be like saying, okay, you get measured down and I get measured down. They cannot do that. So it's, again, it's very strange, but it's something that it's formal, like, and this specific example, it satisfies those things. So it is not the case that from the beginning they should be up or down. So it is completely undetermined until you decide to measure. So what that means is that once they're very far apart, they both have access to this thing. Where is this thing? And how are the electrons getting access to it?
That's very interesting.
Yeah, because it's, and I don't know, have you listened to Michael Levin?
I don't think so.
No, he's a biologist. He's a man. You should listen to him. He's doing very strange experiments on biology, and he argues that I don't remember the species, but there's like two species of animals that only go like their eggs only harvest at every like 7 years, and the others like every 13 years. Now, why? Because apparently that allows them to avoid like when there are predators. But what is the importance of 7 and 13? Well, they're prime numbers. So that means that if you do this every 7 years and the other one does it every 13 years, they will never coincide. So it's like the math is telling these things to behave like this. And somehow natural selection found this thing. And what he's saying is there's a Platonic space of math that is acting on our universe in a way, right? Even living things. And I think this is something like that, right? So this is just math, but the electrons have access to it. Or the other way around, like this thing is acting on the electrons. From where? From Platonic space.
That's a different kind of Platonic forms interacting with our world, because the math example, some people would argue that math is like true, it's like a eternal truth, versus this system almost feels like there's a wormhole or something. Like the connection between
Yeah.
the information feels a bit more direct, or feels more like it's spatially doing something than just in Platonic forms almost.
Yeah, I think there's somebody else. I think it's Brian Greene, a physicist, who I don't know if it was him, but I heard him mention this, that one of the theories to describe entanglement is by using general relativity. And he's saying is this thing, this electron can create a wormhole and the exit is there. So now they're linked instantaneously. So they don't need access to this thing.
Now, would it be then correct to say, so like, yes, we cannot communicate information, but would it be correct to say that something is communicating at a really long distance? Like there is some connection at a distance?
There is some connection at a distance.
Wow.
Yes. Yeah, for sure. But how does that work? How we can use it for something useful? Please let me know if you find it.
So we do know that there is faster than speed of light communication. We just can't use it.
When you say communication, so what?
Well, I don't mean us being able to communicate at all. I mean that there's some type of communication that happens faster than the speed of light, or over longer distances than a point moving at the speed of light from the two spatial points would be able to do. There is, I mean, I'm not sure. Is that a correct thing to say, that kind of communication does happen only between the particles themselves, or the
so that will require. So the problem with invoking things like words like is you need to introduce the notion of information theory, at least the notion of bit of information. And these things,
right,
is like they're sharing a bit of information, right? Because like what's the bit of information? Up or down? Right? 0 or 1. And this says, okay, I'm being measured as down. Okay, so I send a bit on like that is down. And then this one receives it and says, okay, I'm going to be measured down. But that means you're sending information faster than light. And that is not possible. There's a mathematical proof for that. But you have to buy both quantum mechanics and special relativity for the proof to work. And these are like the two of our best theories. So it's like, so it's not like they're communicating in that way. I don't know what it is. And I seriously think that if you answer that question, you get a prize. So it's, yeah, because like this idea of the wormholes, like there's a wormhole here, there's a wormhole there, then they can communicate and it doesn't break like causality. That's the theory, right? They're trying to explain it like that. But you need to be able to set it up for an experiment that you can test, that is falsifiable. And if you get it right with your theory, then you get the prize, right? So far, we don't have that, as far as I understand.
This is very, very, very interesting.
Very strange. Yeah.
Yeah. How long have you studied this? Because you clearly understand it very well, and you are able to explain it very well.
It's been 6 years since I work here, but my so I did okay. Let me start at the beginning. So I was 15, and I illegally downloaded a documentary on string theory, and I clearly remember someone saying that the best physicists are the ones that understand the math.
Right.
And that could be true. Maybe it's not true. But I was 15 and I believed it. So I went and studied math, like pure math. I did a bachelor's in math. Then I did a master's degree, pure math. Then did a PhD in pure math. Then I tried to move to AI. I did a postdoc on AI. And then I was here in Sherbrooke in Canada. And I was here with my wife. And then I got a postdoc in Germany. And we talked and we said, okay, I don't want to move anymore. Like, let's look for something here. And then I found out that there was the institute in which I work right now is the Quantum Institute here at the university. And they were offering a job. I applied and I got it. And I got it because I knew the math. So I had the experience with high performance computing, supercomputers, because I was doing a little bit of AI. And I knew the mathematics of tensor products because that's what I studied on basically in every one of the theses that I wrote 3 theses, one for bachelor's, one for master's, one for PhD, and all of them involve like generalizations of tensor products. So I knew this already. So when I moved. So when I started this job, which is in quantum computing, they started like giving me things to study, and I was like discussing with my colleagues. And it was, at the beginning, it was really strange because, like, okay, I'll start criticizing physicists now. So, because when they talk, they try to say things like and this is one of the things that this paper that I told you, like on the reality of the quantum state, criticizes, is that when you like casually talk to a physicist, they do not decide on the ontic perspective or the epistemic perspective. For them, it's both. You really have to push them for them to decide. And at the beginning, I didn't know how to do this. So, and at some point, I don't remember when, it just clicked. Like I saw a lot of lectures online. Like there are like free MIT courses. I was reading books. I was talking to everybody here, and yeah, watching like random YouTube videos too. And then at some point, it was like, okay, like I started saying, okay, It's not ontic. It's completely epistemic. And I treat it like that. That's the point of view of every scientist that does research in quantum mechanics. You shut up and calculate, right? Unless you are on the foundations of quantum mechanics, then you start thinking, okay, is it ontic? Is it epistemic? And you do this like kind of thinking that we're doing. But if you're doing like research, if you want to develop technology with these kind of things, you need the epistemic because that's the only thing that predicts outcomes of experiments, but via probabilities. So yeah, if you marry the epistemic side, then for sure you'll get a job. And it's not only until like this time that I'm like, because like with time, yeah, okay, I started getting it, but then some of one colleague was just hired, and he came up with this really good like thought experiments on like physical systems. He was saying, okay, quantum mechanics is telling us this, and that. Then where is the particle? And things like that. Things like that you can pinpoint like in the board, and it's like, okay, so what this is saying is that if I detect the particle, then it moves faster than light. So the velocity goes to infinity. What is happening, right? So and we were started like discussing these things like on the hallway or like in between meetings, and it was like, okay, this is very strange. I didn't know this was like something that you could think about. He recommended some papers, and then I started like thinking about all of this. So yeah, I could say that I had an advantage. So it's been 6 years, but when I started, I already knew all the math. Like I haven't learned any math since I started studying physics. So that was really helpful.
I got two questions. One is because you mentioned before that you had an issue with Jacob Brandis's model, so I'm curious about that. The other thing is wondering. It sounds like you're like really deeply understand quantum physics. Is there because what people in the woo-woo community want quantum physics to do is like everything. So if there's like a spiritual connection or like something telepathic, they're just like, well, it's just quantum physics solves that because it's like we don't know, and it communicates faster than the speed of light. So the way it's used in pop culture is really, really poorly, but is there a magic to it at all? Or is, like, do you see like the research potentially leading to us to innovations which seem well beyond the capability of classical physics? Because quantum computers right now are not particularly amazing, I don't think.
The quantum computing? No, not for the things that. So, okay, let me clarify that because that's my job. So, quantum computing works for two things. One is breaking encryption. So the encryption that we use for credit card payments, like that can be broken with a quantum computer. We are very far away from building a quantum computer that is able to do that. We need at least like millions of qubits on a quantum computer, and we are like at 100 right now. And this 4 million needs to be perfect qubits. Our 100 qubits are very noisy. So we are decades away from this. That's one thing. Another thing, which is why I'm here, is quantum computers are physical experiments. For instance, and do remind me about the other question, but let me set this up first.
Yeah.
There's this idea that you cannot mix quantum and gravity, right?
Yeah.
Now, how in the world, how would you even build an experiment that involves both, right? Quantum mechanics, and not only gravity, but general relativity, right? You need to build an experiment in which these both can be brought together. And there's one, at least one that I know of. Let's say you have the Earth here. The Earth is a massive object. It curves space-time. So here, there's a curvature of space-time. If you go far enough in space, then this curvature gets a little bit flattened, right? It may be like a little bit curved, but not as much as when you're close to the Earth. So what you will do is you put a quantum computer here on Earth, where the curvature of space-time is considerably high. And you put another one in space. But now, these two quantum computers need to have what we call as quantum internet. Now, quantum internet sounds as like I'm going to replace the internet that we use with this. It's not like that. Quantum internet is just a word for communication between quantum computers. You need to be able to do like quantum operations on both sides and things like that. Things you do with internet on classical computers, but on the quantum computers. And quantum internet works via entanglement. So these two will be entangled. And now you have a quantum system in different places in which the curvature of space-time is different. And now you can make experiments to test what happens when you put the two things together. And this is different than sending photons or things like that, because quantum computers, like we have specific types of quantum algorithms that are very precise, right? They don't do anything useful. They don't solve financial problems. They don't solve molecular problems, but they're very good for this type of setting. If we do this, we will be able not to solve completely what happens between quantum mechanics and general relativity, but we will be way much more closer with this than with anything else we're doing.
So that's something that's actually going to happen potentially once they build quantum computers that are stable enough that they can do that.
Yeah, and for this, we don't even need that many qubits. So for Shor's algorithm, to like break encryption, we need millions of physical qubits. For this, I think we need like 20. But there's still the misery. We need to be able to build quantum internet, put a quantum computer in orbit, hope that it's going to work when it's in orbit, and put it together, like connected with this one. Right? So there's a lot of engineering happening there, and there's not much funding. So
that is amazing. That's kind of the first thing I've heard about quantum research where I'm just like instantly like, oh, I see exactly what the benefit of that would be for sure.
Yeah, exactly. Yeah. But the thing is that there's a hype, right? Saying, oh yeah, quantum computers are going to replace data centers, and I'm gonna do quantum AI, and it's gonna be better. It's not like that. Like a quantum computer is a computational particle accelerator. Like you don't see people using the particle accelerator to solve industrial problems, right? It's a scientific device. That's the quantum computer. It's a scientific device.
That's very cool. Now, the other question was Jacob Brandes. You had disagreements with his model.
I have disagreements with his model.
Yeah, I thought you said in the message that you don't agree with him. I could find the message.
I don't. I think you phrased it differently right now. Like before, I started talking about this.
Oh, okay. Maybe I just misunderstood then. Okay, it would take me actually a bit because on the computer I don't have enough history to go back actually. And oh, hold on, it's right here. You said I've heard of Jacob and I kind of disagree with him.
Okay, but I think I put it like very generally.
Yeah, you kind of disagree with him.
Okay.
Yeah.
Let me see. Let me find one thing. It's not entirely that I disagree. I'm just I'm not sure. You know? And yeah, because one thing he's trying to do is I think one of the first paper, haven't read the paper, like I just heard him talk about this, is he's trying to get rid of something that we call Markovianity. Now, what is Markovianity? Markovianity is, let's say you have a system, could be quantum, could be not. Let's say, actually, let's go back to throwing a ball. What we say is that this system is Markovian if, like, at the next time step, it depends only on the previous time step. So for instance, let's say I discretize my times in seconds, so I can only measure like up to seconds. So this is second, I don't know, second 2. And at second 3, I see it here. And Markovianity means I can compute this one solely from this one. Okay. And what Jacob says is you should include more things. So that will be like getting states that are there, and all of them tell you what is going to happen after.
Really?
Yeah, that will be something that is non-Markovian, because Markovian is just like from where I'm sitting to the next step, like I can predict that. Non-Markovian means you need to add more things, not just like the present, but also the past.
Oh, I thought his model was more about like if you have, like with that example of the ball, if you zoom in, you'll see that every single point between them it can be filled. It'll have, there can be a you can set t time to that where it will be anywhere on the line, versus I thought he was getting rid of that aspect in relation to quantum physics. So he was saying that the particle doesn't precisely travel, it just stochastically does a probability distribution, and then the next measurement it's there. There's like no in between space. I thought that's what he was saying.
Yes. So first, you just made a metaphysical claim. You said that time is continuous. So, but we don't know, because the way that we measure time, it only gives us like discrete steps. And that's weird, because like, again, that's another big questions of physics, is like, what is time, right?
Interesting.
We don't know what time is, but we can measure it very precisely. Like we can zoom in as far or like as close as you want. But once you do that, you don't see a continuum of times. You only see discrete places.
Interesting.
So yes, if you take this like metaphysical statement that time is continuous, yes, I agree with you, but we don't know. Right? And this is something like all over physics, like every physical theory assumes time is continuous.
Man, it's very, very interesting talking to you. I've never been able to like sort of, say something and then actually get a response directly relating to the thing at that level. I get a feeling when I'm talking to you like I'm approaching this mysterious thing of quantum physics in a way that I've never in the past done, where I'm way out from understanding quantum physics, but I feel like now maybe I'm closer to knowing some true things about it, kind of.
Yeah. And oh yeah, I think I remember some other thing that you said. Something about the Wu, right?
Right.
For quantum mechanics. Yeah, that's actually has brought me like personal problems, like knowing quantum physics with things like uncles or my aunts. Like they start talking about the woo, and they say, "Oh yeah, because quantum mechanics." And I said, "Actually, no. Like that's not how the math works, right?" So yeah. So for instance, let's say one of the misconceptions is that it is consciousness that collapses the wave function, right? So if I give you, how can I put this? So at some point, you have to decide what you're going to measure. For example, let's say I have a spin, psi. And you remember that we were putting this C apparatus or the Y apparatus, and these are called like Stern-Gerlach apparatus. So this C and then putting a screen, and the Y and then putting the screen. This whole thing is a quantum measurement. All of this. So here you have to decide what you're going to measure. Are you going to measure C or are you going to measure Y? Who decides that? You need consciousness for this, right? An agent has to come and say, okay, I choose this one, I choose that one.
Right.
What other way do we have to do it? Maybe I throw a random number. What is a random number? Like I throw a coin? An agent has to do that, right?
Right.
And if you believe like the classical physics, throwing a coin is deterministic, right? The only variable is I decide how to throw it, when to throw it, where to throw it, the force, the speed, right? But once it leaves my hand, it's completely determined. Like in principle, I can solve all the equations and I know what is going to land. So it's my consciousness that is driving this. And it's my consciousness that is deciding these two things. So let's say, like indirectly, right? So if I decide which one I'm going to measure by throwing a coin, it's actually me who's deciding, right? Like indirectly. So what other ways do I have to produce random numbers? Is on a computer, on a classical computer. I take a random on NumPy, right? But there is not an actual random number.
Right.
You're a programmer, so you know how this works. So these are like absolutely deterministic that produce like from a seed, and then what you do is you fix the seed, then you always get the same random number, right? But these are like pseudo random numbers. So that's still not a random number. How do you get an actual random number? From a quantum experiment. And that's one of the applications of quantum mechanics, producing random numbers, like actual good random numbers, not pseudo random.
As random, I mean, as far as we know, because we also don't know what's happening under the surface. Also, when it comes to consciousness, could the quantum give us free will because we don't know what is determining certain things?
Very interesting question. Look, this paper that I'm reading, it makes assumptions. The first assumption is quantum theory is right. It assumes quantum theory. Then it also assumes that, because right now, quantum theory tells you there's a quantum state. We don't know if this quantum state is in the universe or if it's like only on Platonic space, right? Or what's the interaction between the two things. But what this paper is assuming is there is a physical state that is not the quantum state. It could be the quantum state. The quantum state is probabilistic, so it only gives us like some like information about like uncertainty of what we do. But let's assume there is an actual physical state, but we don't know what it is, right? We don't have access to it. We just assume that it can exist. So there exists a physical state that is deterministic, all right? So I produce, let's say, like for the spins, let's say quantum theory tells us my spin is on a superposition of up and down. And I measure, and sometimes gets me up, sometimes gets me down. What this is saying is if you produce your spin in a superposition and you measure and gives you up, then you can reproduce the experiment and it gives you down. But you think you did the exact same experiment. But there's something else happening. You don't have control over it. You don't have way of knowing what happened, but it actually produced the other one. Right? So that's this thing. So you assume this is what is happening. There's something else happening there, and you don't know what it is. You don't have control over it. And the third one is my favorite. Is free will. Why? Because with all of these assumptions, the authors build an experiment in which you have a gun here, and it's going to shoot like either one of two quantum states, right? They say the 0 and the plus state, and then here you send the 0 or the plus state, and they say these two are going to be set up independently in a non-correlated way. So that means that you need to find a way that this produces something that is uncorrelated to this. And the only way we know or we believe we can do it is if you put two people that do not communicate between them with free will, one here and one there. One decides which button to click here, and the other one decides which button to click here. But these two needs to be independent. So that means that the subjects that you put there have free will. And that comes out like later on the proof, like you need independence for some of the variables, because there's another thing in probability theory. So there's like the probability of you have two random variables. So like the product of the two, if these are independent variables, by the laws of probability theory, this is the product of the probabilities. And you need this for the proof to work. And what they do is, they say, if you have this setup, then the quantum state is on it.
I don't really understand. Like,
which part?
so I mean, I was following until I think until you wrote down the equation. So P xy equals P x. So the probability of xy. Those are two different quantum states. So the two equations say what do the equations do that related to the firing gun?
Oh, okay. Yeah, maybe I went too far. So listen. Let me start over. So you assume quantum theory. Quantum theory is the postulates and that they predict probabilities, right? Second thing is that there is a physical state, right? You don't know about it, but it is there. And the third one is free will, because they build an experiment in which you need to put agents there that each one of them has free will to decide which button to click on the devices. Now, at some point in the calculations, there's something like this that you have to compute. Now, this one is like the decision made here, and this one is the decision made here. Now, if you assume free will, that means that these two are independent. So the choice of this agent and the choice of that agent are independent. If X and Y are independent random variables, by the loss of probability, you have this. And now that allows them to do more math. And with that, they're able to conclude that the wave function, the quantum state, is ontic.
Right. Now, that's very theoretical, though, right?
Yeah. And you need to buy these things. Like, okay,
Right.
let's go over that. Like, what do you buy from me? I buy quantum theory. Like, free will, I'm not sure. But let's say I buy free will. And now I also need to buy that there is a physical state. So
But that one just seems difficult to do. So like, isn't this, you're running an experiment based off an assumption that there's a physical state, and then but like, how can you run an experiment off that assumption? Like, you'd have to first prove that. You have to know that, right?
it's a thought experiment.
Right. Okay. Yeah.
Exactly. Yeah. And the thought experiment is something like this. Like, you have two cannons with two different, each one can fire two different quantum states, and somebody makes the decision of which one to send. Right. And these are actually like spins, qubits. Qubits are spins. So, and then they do like the math precisely, and they arrive at the right conclusions. But yeah, there is like a lot of things. Like, precisely for two, it's they say, okay, let's assume physical state there. We don't know what it is. And they assume things, they assume properties of these physical states, some mathematical properties. But
Right.
But why? We don't know what it is. Why would you put extra assumptions on these things?
Right.
And they need that for this proof to work. And it is like that for every proof that involves physics, right? Your assumptions need to line up with things that are grounded in the universe.
Otherwise, they're just like, well, what do you think about string theory?
String theory?
Yeah.
Very nice math. Yeah. It's very similar to what I was doing on my PhD. Actually, for my PhD, I started studying string theory from pure math because they're doing very interesting math. But then I got caught into AI and then quantum. So,
but I think it's yeah. You go.
No, you go.
Oh, because it's been, I think it's been as far as what I've seen, a trend to sort of diss string theory. Say basically it's not, doing what it accomplished. But that's interesting that you say that the math is very beautiful, because that means on an aesthetic level, and I mean aesthetic it can say a lot for scientific proofs. Sometimes the aesthetics of something can validate it, but that's interesting you say it's very beautiful math.
So the math is beautiful, but that's also I don't remember the title of the book, but by Sabine Hossenfelder. I don't know if it's Beautiful Math or something like that, or no, Trapped in Math, something like that. And she does like an investigation. She does like goes and interviews like very important physicists, and she like poses like these questions, like, okay, like string theory is beautiful. Like, I think he goes to supersymmetry, whatever that means, right? It's a kind of theory. And supersymmetry was developed because it was beautiful, mathematically, right? But what she's trying to argue is we're not looking for beauty. Like, beauty is human. It's we humans who decide what is beautiful. But we are nobody to tell to the universe how to behave. right? Not because it's the most beautiful theory, it has to be true.
Yeah, I mean, like beauty can like direct our path, but I mean, I think it's a very clear mistake to assume something's true because of its aesthetic, especially in physics.
Yeah.
Um,
And no, and there are like very like beautiful things in physics that are completely unexpected. Like harmonic oscillators.
I know what that sounds like.
Yeah, exactly. So a harmonic oscillator is a pendulum, right? You plug it here, you let it go, and it's gonna start to oscillate.
Right.
Another way to do it is you put like something here that is frictionless. You have a mass, and then you have a spring, and you attach it. So you pull it, and then you let it go, and it's gonna start to oscillate.
Right.
And these things have equations, like differential equations that define that moment. But then, like you go and you build electrical circuits. For example, you put two plates like this together. That's called a capacitor. They don't touch, but they're very close. So that's a capacitor. Now you go here, and then the same cable, you do a coil. That's called an inductor in this electrical circuits jargon. But it's just doing this with the coil. Now, what this means is, what this is going to do is, when you pass electricity to it through the coil, it's going to create a magnetic field like on the inside of the coil, and it has some nice properties. But now what you do is, you plug this thing together, and you add electricity to it. The equation that describes this is exactly the equation that describes that.
Yeah, that is nice.
But this is gravity.
Mm-hmm.
Like, drives the pendulum is gravity, the force downwards. And this is electromagnetism. And it's the same equation. Like, you just change the variables. Like, there's a variable here for the capacitor that depends on the area of the plate, and this is how many times you draw the coil. But in this one is like the length of this thing, how far you start, like the mass of the thing, and you rearrange these terms, and it's the same equation.
It's like what, like a sine wave, basically.
So I think sine is a solution for the equation. Yeah, something like that. Yeah. But do you see what I mean? These are very different things. And
Yeah, they're different. I mean, to me, I feel like maybe this comes from my game programming sense, but like anytime I'm programming physics in a game and I have like two objects, what I use is like iterative, physics where they just slowly like push each other apart. And like that kind of physics system tends to just sort of like generate the same type of things across, the field. Like, so it feels to me, it feels like those things would be the same because it's just like you have like with that spring thing, like is that like a spring that has these things that are like connected and they can is the oscillation of this thing with the spring a physical oscillation?
You mean here?
No, this one down the bottom one here.
This one?
Yeah.
No. This that's exactly the point. Like, this is not physical oscillation. This is electromagnetism.
Oh.
But when you write down the equation, it's something like here there's a mass, right? I don't remember the equation, but here you have the mass, and here you have like the charge of the particles moving in this electrical circuit.
I see.
In the equations, you exchange the mass for the charge.
I misunderstood that. Yeah, okay. That's an interesting coincidence.
Yeah, exactly. Yeah, it's it's strange because mass is really important for gravity, and charge is really important for electromagnetism.
Mm-hmm.
And the way that you go from one differential equation to the other is by replacing one for the other.
Are you familiar at all with Wolfram, Stephen Wolfram? So he has this idea of like, oh, one thing he was interesting that I was saying was just such a revolutionary concept to me. The maybe the topic or the header of what he was saying was, why is the reality 3 dimensions or 3 plus 1 dimensions, what he was saying. And what he was proposing is that it's only 3 dimensions because of our observation. Because, I mean, you can even think about things in reality that don't really experience reality in 3 dimensions. Like the internet is really, it's definitely not 3 dimensions. It's just like information travel. And so what he was saying is that, maybe from a different perception, if you were like maybe much larger or much slower or much faster, reality would not appear 3-dimensional.
Uh-huh. I'm aware of some of the things he works on, but I'm not sure I can comment on how he interprets, how he thinks about these things. Yeah, but I also know like he has like a theory of the universe as a computational graph.
Right.
And if I remember correctly, don't quote me on this, but I think he's assuming that things like time and space are not continuous. You remember that I told you that time could be discrete because that's what we measure.
Yeah. I'm pretty sure I think his theory is like hypergraphs. So he thinks everything's happening in hypergraphs. So it's not continuous. Yeah.
I think that's where the hypergraph comes into play.
Right.
This comes in like bits of information, not like a continuum.
Yeah. And I think, says that physics isn't something that can be described by math because he calls it computational irreducibility. There's some things which can only be determined by running the computation itself.
Yeah.
You go.
I forgot to answer your question about the Wu. Yes. Okay. Well, I think that counts as Wu because it tells you like free will is kind of linked to quantum mechanics.
Mm-hmm.
Right? But
right.
Have you heard of the Wigner's friend experiment?
No. Maybe I've heard of it, but I forget the name at least.
So Wigner is a physicist, and I don't remember if he was the one who came up with this or he started asking the questions and then somebody else like put him in this experiment. But the idea is you have a person that is isolated from the universe, right? For example, let's put a scientist playing with a quantum computer, right?
Right.
So
I think I may have heard this one. This is maybe the one where the person watching the quantum experiment is themselves being watched.
yes, exactly. Yeah,
okay.
yeah. Then there's a quantum computer here. And they're like isolated from the universe. So here's a quantum computer, and there's only one qubit there, a spin. And the spin is in a superposition, right? So the spin at this moment is 1 over square root of 2 up plus 1 over square root of 2 down. That's Wigner's friend. Wigner is here. Now, this person measures the qubit. It's going to be up or down, right? But the postulates of quantum mechanics do not answer the following question. Did the qubit collapsed? Did the spin like collapse to up or down? Or is the person who reads the result now in a superposition too? right? Because for the person outside, this is the quantum system. That everything inside here is a quantum system. So it could be that this person measured up or it measures down. So now you have like two things that kind of like coexist, right? So the person could have measured up or could have measured down. But what is actually happening is a state of this form, but now it involves a person. Now you open the door, right? The qubits are already measured, and there's no way that the information of the measurement can come out of the room without this person saying the result of the measurement. Okay? So you open the door, and this person comes out. What's the wave function? Is this still this state, or this state already collapsed? Or will the state collapse when this person says, I measured up? Right? Is that like, or is the wave function collapsing when the person decides in his brain that he's going to say what he measured? Or when he starts saying to say up, or when he says or down, like at the beginning of the word, at the end of the word, like when the electrical signal it's sent to like produce the word, when is that collapsing the system?
Could there be restrictions on the possibility of such an experiment in reality because of what it takes to actually have a system be quantum? Because in your quantum computing, you have to have them in like super cooled and stuff. And so like this person in the box would have to be super cooled, like the edges of the box would have to be floating so there's nothing touching the ground. Like would it maybe it'd have to be in outer space or something? Like
no, not necessarily. So actually the quantum computer will be like closed in itself, and he has access to the results via a computer that is not connected to the internet, right? There's no way of communicating with the outside world. So there's here like a computer, and this computer is connected to the quantum computer and is doing the measurements via some electrical pulse that he sends to the quantum computer.
Right.
So yeah, he's not at cryogenic temperatures.
Yeah, but I'm just thinking like, wait, hold on. So like, but he himself is also in a quantum system, right?
Yeah,
Because
he's not communicated with the outside world.
He's been separated from the outside world, but I'm just asking, like, you know, what would it actually take to physically do that? Because I mean, it sounds like in your quantum work, in order to get something to be quantum, it's like really difficult, and like, so like in order to get a whole person in a state which is quantum, I mean, I know it's a thought experiment, I know it's not physically, but I mean, the reason I'm asking is because what I'm wondering is like, is something that causes decoherence the collision or the nearness of electrons in physical space? Because I mean I guess then you could maybe put this in outer space and then
yes, listen, the decoherence is difficult to understand. I don't understand decoherence. Like I've seen explanations of it. Things like you have your quantum system and it's like colliding with other particles and it loses its quantumness after a while, but that doesn't seem so rigorous. There's other ways to explain decoherence. There's a theory called quantum Darwinism, which says that the quantum state is at a superposition, but that means that every particle in the universe can be in a superposition. For example, this wall, right? So this could be here or there, according to the superposition equation. But how is it that it's here every time I look at it, every time I touch it? Is it like, where's the superposition? Like, there's no quantum behavior like in our everyday lives.
that's where you get into like the many worlds interpretation, right?
That's interpretation. Yeah, exactly. Maybe there's another interpretation. Like, yeah, for example, like, let's say you have the same experiment, right? Me, I'm working on the lab, and I'm measuring 1 qubit. If it's measured up, I close my computer and I go home. If it's measured down, I wait 5 minutes more, right? But it turns out that if I measure up and I go home, at exactly that time, a truck hits me and I die.
Right.
Right? So what happens if I measure down? I wait 5 minutes and I go home completely safe, right? But what determines that? Now, what the multiverse hypothesis says is actually both happen. So the universe splits, the wave function does not collapse. The wave function is still in a superposition of up and down for that particular bit of information. And in one of the universes, it is up, and in the other one, it is down. In one, I die, and in the other one, I don't. That's another interpretation. Now, for this one, you need to assume that the measurement, so the measurement gives you either up or down, right? But what is the measurement? The measurement is something that you plug into your quantum system. Like, it could be a cable, it could be something. It assumes that the measurement is not collapsing, that the measurement is entangling, like the measurement with the quantum system. But again, this is not in the postulates. This is something extra that you have to buy.
It's a guess.
Like the pilot wave. Yeah.
And it seems expensive. Like, I know Stephen Wolfram likes it. I mean, I also even had a thought that I thought was quite interesting relating to that. I thought, well, when it comes to evolutionary biology, evolution is very, very effective at moving creatures towards intelligence. And I thought that one thing that could maybe enhance that, because it seems extremely rapid. I mean, it's millions of years, but it just seems very, very effective at that. One thing that could almost be like a guiding force, like a kind of a God arm in reality, leading it towards something, is if you like imagine a metaphysics where it is multiverses. So it's just like, just sort of not infinite, but a huge number of multiverses splitting out. And then reality itself is selecting for that multiverse, which is the most abundant or high in number. So like, you think the person has a decision, they decide to go here and here, and then both happen in a different reality, and they both play out, maybe even 100 years in the future, both play out. And then the other one, just every single one that didn't have as many things going on, died out, which would explain this sort of ever increasing complexity of the universe. Now, I don't necessarily think that's true. I just thought it was interesting.
Yeah.
Hypothetical.
Yeah, it's because like even here, like, you still have the possibility that this person measures, he goes out and he tells nobody about the result. Does that mean that this person has like a double existence? Like, he's coexisting in during like the rest of his life with the result only in his head? Well, in his mind, because he saw the result, right? He knows the result, but that result is in his mind. Is the mind part of the universe? If the mind is part of the universe, can it be entangled? Can it collapse? How does collapse looks for the mind? The mind, the consciousness, whatever. So this is like very, very weird. And again, like, quantum mechanics allows for these things, but it doesn't tell you what happens.
They haven't found quantum systems in the human mind yet, have they? Like they maybe have thought it was the microtubules that maybe were quantum systems, but it's never been like proven, right?
Oh, yeah, that's also a very interesting question. Yeah, there's some theory about microtubules. I don't know much about that, but I do know one thing about microtubules. What is it? Okay, so microtubule is a tubule like that, and it has a length. Okay, I can measure this length. Let's say it's L. It turns out that the brain, so where these microtubules live, there's a lot of other things going on. Right? There are electrical charges. There are a lot of proteins. There are like a lot of ions moving. It's messy, right? It's wet, and everything is happening at the same time. So what that means is that the process of decoherence, so when a quantum thing becomes classical, is very fast. For example, that's why you need to isolate quantum systems for they to be able to live longer. So if you do the computation here on a microtubule, and you say, okay, I start here with a quantum state that is actually in a superposition, right? It needs to travel this distance. But due to all the things that are happening, when it goes out, it's going to be either down or up. Let's say it's a spin. So what it's saying is, even if this L is able to maintain some kind of superposition, after a while, the system will collapse. And the quantumness will not live through this. And this is a calculation, I think Max Tegmark did a paper on this. He did the explicit calculation for this, for microtubules. Like he took the length, he took the equations for the coherence, he solved everything. He said, okay, there's no way that a quantum computation can be done with this. Right? But it's different. Quantum effect from quantum computation. For quantum computation, you need this thing to survive at the end, like the superposition, and to be able to operate with it. So, yeah, but there could be like other quantum effects happening that do affect like consciousness or free will.
In reality, how much is quantum physics happening? Because you're saying the conditions are strenuous for a quantum thing to actually happen. So if you look at like just the material world, can you like categorize like, well, in this type of environment, there's going to be more quantum physics, and in this environment, you're going to see very little?
Yeah, for example, computers. So everything that involves like electrons and like transistors. So transistor is a small quantum system, right?
What?
So
Really? Like
yeah,
a regular transistor is?
yeah. So it's not that the rate is probabilistic, but the way that it works is because you're able to write down the quantum mechanical equations, and you know how to turn out like how to turn the probability that once you close the transistor. Okay, let me do that. So a transistor is a switch, right? So it's either on or is off. But this is actually like a small plate like this. And this thing will allow electricity to pass or not. If it allows electricity to pass, then it's going to be on. If it doesn't pass electricity, then it's off, right? So this will be bits of information, 1 or 0. And you're able to turn the probability that there's going to be electricity there to 0 because of quantum mechanics. Because you can write this thing down in quantum mechanical ways, and then you minimize the probability. Actually, It's not exactly 0. It's minimized. That's why you have numerical errors or things like that. Like if you work with your computer for a while, then it starts to get buggy, and you say, okay, I need to restart my computer. It's because
Interesting.
these probabilities turn out to be not
Wow.
zero. And some of the bits were up when they were supposed to be down.
Wow.
So it's not entirely 0, but it's like minimized as close to 0 as possible. And that's done using quantum mechanics.
That's so cool. That makes so much sense because yeah, computers do have that quality where they sort of like seem to get weird. Yeah.
It looks like it comes from nowhere, right?
Right.
But it comes from somewhere because the probability is non-zero. The quantum mechanical probability is non-zero.
Wow.
Yeah. Oh man, how long have we been here?
Yeah, it's been 4 hours, 4.5 hours.
Oh man, I really thought it was like 2 hours. Okay, let's quit now.
Yeah,
That's what
that
I'm
was
getting.
that was absolutely amazing, man. That was really amazing.
Thanks.
Thank you.
Yeah, for sure. And anytime, just pin me if you want to continue on something, or if you find
I,
like questions about anything, send me a message. I'll try to clarify.
fantastic.
Yeah, for sure. And I'll work on this small example on Schrödinger's equation
Cool.
to try to like explain it like really like in detail. So you
Cool.
can see
That'd be
that
great.
when ontic is equal to something that is epistemic.
Yeah, I'd like to see that.
Yeah. Me too. Never done that before. Okay.
Fantastic. Yeah.
Thanks
I'll
for your
see you
time.
later. Absolutely.